We'll begin our study of electricity and magnetism by looking at charge, which is a fundamental property of all matter, given that matter is composed of atoms. And charge is a scalar quantity and described as either positive or negative. And now if we consider an atom here, it has a nucleus, and this nucleus in the middle is made up of protons, and a proton has a positive charge, and a nucleus is also made up of neutrons, which carry no charge. So these particles are referred to as nucleons, and orbiting the nucleus are electrons, which have a negative charge. So the magnitude of charge of a single electron or proton is called the elementary charge, and denoted E, which is 1.602 by 10 to the negative 19 coulombs. So effectively this is considered to be the smallest indivisible amount of charge. So effectively charge is quantized, so it's a multiple of an elementary charge, and denoted by Q. So in other words, the charge of an electron is minus E, and the charge of a proton is plus E. And again, the neutron has no electric charge. So a point charge is a model where the physical size of a charged object or system is negligible in the context of the problem being analyzed. And we'll look at this in more detail as we progress. Coulomb's law describes the electrostatic force between two charged objects. So suppose we have a charged object 1 and 2, then the magnitude of the electrostatic force is proportional to the magnitude of those charges, so Q1 and Q2, and inversely proportional to the square of the radial distance between them. And Coulomb's constant is the constant of proportionality, and it can be written in terms of the permittivity of free space. And we'll look at the permittivity of free space in more detail later on, and this form of the constant makes it more convenient to analyze spherically charged bodies. So given that the force is in newtons, then Coulomb's constant must have units of Newton meters squared per Coulomb squared, because the charges each have a unit of Coulomb, and the radial distance between them has a length unit. So electric forces are one of the forces that hold the structure of an atom together. So for example, we have attractive forces between the protons and the electrons, whereas a nuclear strong force holds the nucleus together. And when we refer to charged objects, we can refer to charged bodies, ions, and so on. So for example, if we pop off this electron from the lithium atom using electromagnetic radiation, then we get a lithium ion, which we can treat as a positive charge. And similarly, if a chlorine atom gains an electron, we have a chlorine anion, which we can model as a negative charge. And these would exert an electric force on each other to form an ionic compound, being lithium chloride, which is electrically neutral because the positive charge cancels the negative charge. Now the direction of the electrostatic force depends on the signs of the charges of the interacting objects, and it acts along the line of separation between the objects. So if we consider this as a radial vector from charge 1 to charge 2, then we can write this electrostatic force in vector form, being the electrostatic force exerted by charge 1 on charge 2. So we talk about this force over here, and that's equal to Coulomb's constant multiplied by charge 1 and charge 2 on the square of the radial distance between them, and multiply by the unit vector from charge 1 to charge 2. So that will be this unit vector over here. And this unit vector is the vector r normalized by its magnitude. So two objects with charges with the same sign exert repulsive forces on each other. So as we can see, if charge 1 and 2 are both positive, so we have the unit vector pointing in a direction from charge 1 to charge 2, and therefore the electric force of charge 1 on charge 2 acts in a positive direction. So it's effectively repelling charge 2 from charge 1. And in contrast, for example, where charge 1 is positive and charge 2 is negative, so effectively two objects with charges of opposite signs exert attractive forces on each other. So as we can see, the unit vector from charge 1 to charge 2 acts in a direction from charge 1 to charge 2, and this term here will be negative. So the force exerted by charge 1 on 2 will be attractive, or point towards charge 1. Now electric forces are responsible for some of the macroscopic properties of different objects. So for example, if we consider this lithium bar, it's made up of many atoms with delocalized electrons, and these give the bar special properties. So for example, it would have a tensile strength, because if we exert a tensile force on the bar, it's going to break when it reaches its strength. And we know that with metallic bars, we have delocalized electrons interacting with the positively charged core of the lithium atoms, which is known as metallic bonding, to provide certain properties to the bar. But given the large number of particle interactions that occur, it's more convenient to treat everyday forces in terms of non-fundamental forces. So recall the contact forces being the normal force. We have the friction force and the tension force that we mentioned. As we've seen previously, electrostatic forces can be attractive or repulsive based on the sign of the charge, whereas gravitational forces are always attractive. So for any two objects that have a mass and electric charge, the magnitude of the gravitational force is a lot smaller than the magnitude of the electrostatic force. So suppose we have a proton and an electron. So we have the mass of the proton and the mass of the electron here. And note the universal gravitational constant, which we've looked at in the mechanics part of the course. And here we have the permittivity of free space and the elementary charge being the magnitude of the charge of an electron and proton. So if we substitute the charge of the proton and the charge of the electron, which is negative, and the mass of the proton and the electron, and also the permittivity of free space and the gravitational constant that we're given here, and then we'll take the ratio of the magnitude of the electrostatic force to the magnitude of the gravitational force. So if you calculate this out, you'd get 2.269 by 10 to the 39. And note that the squared radial distance between the charges cancels. So as we can see, the magnitude of the electrostatic force is much larger than that of the gravitational force. So gravitational forces dominate at larger scales, even though they're weaker than electrostatic forces, because at large scales, systems tend to be electrically neutral. Recall that the Coulomb force, or the electrostatic force, has a magnitude that's equal to 1 over 4 pi by the vacuum permittivity, or permittivity of free space, multiplied by the magnitude of the two charges involved in the interaction over the square of the radial distance between those charges. Now suppose we have multiple charges that are exerting electrostatic forces on each other. So if we label this charge 1, 2, and 3, and without looking at the vector form of the electrostatic force, we know that opposite charges exert attractive forces on each other, and like charges exert repulsive forces on each other. And the net electrostatic force on a single charge can be obtained using the method of superposition. So effectively summing the force vectors together using vector addition. So the net electrostatic force on charge 1 is equal to the force exerted by charge 2 on charge 1 plus the electrostatic force exerted by 3 on 1. So if we sum the force exerted by charge 2 on 1 and the force exerted by charge 3 on 1, then using the vector head to tail method, the net electrostatic force acts in this direction. And similarly, if we use the parallelogram method, we can draw the force exerted by charge 3 on 1 up here, such that this force and the force exerted by charge 2 on 1 form a parallelogram. And therefore the net force acts from this point to the opposite end of the parallelogram. So therefore we can see that the net force exerted on charge 1 has the same magnitude and direction using both methods of vector addition. And also note that charges 2 and 3 exert attractive forces on each other. So have a go at determining the net force acting on these charges using the same method of superposition. Electric permittivity is a measure of the degree to which a material or medium is polarized in the presence of an electric field. So recall the Coulomb force, which was equal to the reciprocal of 4 pi by the permittivity of free space by the product of the two charged objects on the square of the radial distance between them. So we just take the magnitude of this product, which gives the magnitude of the electrostatic force. Now similarly, the electric field due to a single charge, so for example charge 1, can be written as follows. And we'll look at electric fields in more detail later on, but you can picture it as a vector field going from a positive to a negative charge in this case. So this permittivity of free space is basically the resistance of a vacuum to an electric field. So consider these two charged plates, which are conductors, and a conductor is basically made from an electrically conducting material, such as a metal, where the charge carriers can move easily. So for example, a charge carrier can be an electron or ion and so on. So in this example of a metal, the electrons are delocalized from the atoms and they're free to move around. Whereas an insulator is made from a non-conducting material where the charge carriers cannot move easily. So for example, in amorphous glass, being silicon dioxide, so in this covalently bonded solid, the valence electrons are localized to the covalent bonds, so they can't move around easily. So we can model electric polarization as an induced rearrangement of electrons by an external electric field, which results in a separation of positive and negative charges within the material or medium. So for example, consider this insulator subjected to an electric field. So remember that opposite charges attract. So we can model the atoms as follows, where the electron is drawn towards a positive charge. So the atoms deviate from their spherical shape using a simple Bohr model. So we can draw a few more in here as follows. And you get the idea. So what this does is result in an electric field that opposes this electric field due to the two charged plates. So we can draw this schematically as follows. And we'll look at these insulating materials later on, such as glass, which is a type of dielectric. And the advantage of having this between two charged plates of a capacitor, which we'll also look at later on, is that the electric field resulting from the polarization of the dielectric opposes this main electric field. And that results in more charge being stored on this plate, and that increases the capacitance of the capacitor. So free space has a constant value for the electric permittivity, which is epsilon naught. And as we saw, it appears in physical relationships, such as the electrostatic force and the electric field. And the permittivity of matter has a value different from that of free space, and depends on the matter's composition and arrangement, as we saw. The following static charges are positioned in a square configuration at a distance d from each other. If the net electric force on each positive charge is 0, what is the coefficient alpha of the positive charge? So if we label these charges as 1 to 4, and we look at a positive charge, then we have an attractive force exerted by charge 1 on 2, and an attractive force exerted by charge 4 on 2. And like charges repel each other, so charge 3 will exert a repulsive force on charge 2. And by geometry, given that the length of the sides of the square are equal, then this angle here is 45 degrees. And now if we take a sum of forces in the horizontal direction, and the net force on each positive charge is 0, so that's equal to 0, and we'll take our positive direction to the right. So the force of charge 1 on 2 is acting to the left, so that's equal to minus Coulomb's constant by the product of the charges over the squared distance between them. And if we resolve the force of charge 3 on 2 in the horizontal direction, the horizontal component acts to the right. So that would be plus Coulomb's constant by the product of the two charges over the square distance between them. So this length here of the right angle triangle is the square root of d squared plus d squared by Pythagoras' theorem. So that will be equal to root 2 multiplied by d. So the squared distance between these charges is root 2 squared by d squared, which is 2d squared. And then to get the horizontal component of this force, we take the cosine of 45 degrees, which is 1 on root 2. And that's all equal to 0 according to the problem. So now if we do some cancellations, we have Coulomb's constant cancels, d squared cancels, the charge q cancels, and one of the alphas cancels. So what we have is minus 1 plus alpha on 2 root 2, which is equal to 0. So therefore the coefficient alpha is 2 root 2. And remember, by quantum mechanics, charge is quantized. So the magnitude of any charge is a product of the elementary charge, being the magnitude of charge of a single proton or electron. The net charge, or charge distribution of a system, can change in response to the presence of, or changes in the net charge, or charge distribution of other systems. And the net charge of a system can change due to friction or contact between systems. So for example, if you consider your hair as a system, and you rub a balloon on your hair, then electrons get transferred from your hair onto the balloon, and the net charge of your hair will be positive. So therefore the balloon will be attracted to and stick to your hair due to electric forces resulting between the attraction of opposite charges. So another example is if you wipe a glass rod with a silk cloth, the glass rod loses electrons to the silk cloth and gains a net positive charge. Now, induced charge separation occurs when the electrostatic force between two systems alters the distribution of charges within the systems, and this results in the polarization of either one or both systems. So for example, if you bring this positively charged glass rod next to a neutral conductor, then this will attract electrons towards it, leaving behind a distribution of positive charges. So effectively this system, being the conductor, has been polarized, because an electric field will be generated due to the separation of these charges. So this is basically induced charge separation, which, as we saw, can occur in neutral systems. So in general, any change to a system's net charge is due to the transfer of charge between a system and its surroundings. So therefore charge is conserved and the net charge is constant. So effectively, when the glass rod loses charge to the silk cloth, this is basically a transfer of charge. So charge is not created or destroyed, but transferred between systems. And as we saw, the charging of a system typically involves the transfer of electrons to and from the system. So in these two example cases, and the net charge of a system will be constant unless there's a transfer of charge to and from the system. Consider this glass rod, which is positively charged. So for example, if you wipe it with a silk cloth, it loses electrons. And now suppose we have this conductor sitting on an insulator. And remember that the electrons or charge carriers in conductors are free to move around. So if we bring the glass rod near the conductor, it's going to draw electrons towards it. And that leaves behind a positively charged region. Now if we bring these two conductors into contact, then this positively charged region here is going to be even further away. And now when we separate these conductors, this one will have a net negative charge, and this one will have a net positive charge. So we've induced these charges on the conductors, and this is called charging by induction. Now consider this rod made of rubber, which is negatively charged. So for example, if we rub this with a piece of fur, it'll gain electrons from the fur. So again, if we have this conductor sitting on an insulator, this negatively charged rod will repel electrons this time. And that leaves a positively charged region near the rod. And now we can ground this conductor by connecting a wire from it to a much larger and approximately neutral system, such as the Earth. So therefore in this case, we provided a pathway for these electrons to escape the conductor, so they'll go even further away from this negatively charged rod. And now if we cut this wire and remove this negatively charged rod, then these electrons will have no way to get back. So therefore that leaves behind a net positive charge, and we've charged this conductor by grounding it. And note that this excess charge redistributes evenly on the surface of the conductor under electrostatic conditions. Electric fields may originate from charged objects, as we can see. And now consider this test charge Q. Then the electric force exerted on this test charge due to this charge appears as follows, and is equal to 1 over 4 pi by the permittivity of free space by the product of the two charges on the squared distance between them, as we've seen. So this electric force acts to repel this test charge. So therefore the electric field due to a charged object Q is equal to the ratio of the electric force that's exerted on the test charge at this point to the charge of the test charge, which in this case is Q. So therefore our electric field, due to this charged object Q, is written as follows, and is independent of the test charge. And a test charge is a point charge that has a small enough magnitude such that its presence does not significantly affect the electric field in its vicinity. So as we can see, given that the force is inversely proportional to the square of the radial distance between the two charges, then the electric field has the highest intensity near the charged object, and it drops off according to this inverse proportionality of the squared distance to the test charge. So we can see that the electric field has the highest intensity where these lines are more dense, and where the electric field lines become less dense, the electric field is weaker. So the electric field points away from isolated positive charges, which we can see over here, and if we had a negative charge, then the electric field will point towards it. And the electric force exerted on a positive test charge by an electric field, as we can see, is in the same direction as the electric field. So if we had a negative test charge over here that has a magnitude of 3Q, then the electric force exerted on this test charge points in the opposite direction as the electric field. And therefore, the electric force on this test charge is equal to minus 3Q multiplied by the electric field due to charge Q. So effectively we can place a test charge anywhere in this electric field and calculate the electric force exerted on it as follows. The electric field is a vector quantity that can be represented in space using vector field maps as shown. So as we can see, the vectors in the vicinity of the positive charge point away from it, and near the negative charge they point towards it. So here we have an electric field map for a dipole, where the dipole is two equal and opposite charges. Now the net electric field at a given location is the vector sum of the individual electric fields created by nearby charged objects. So for example, if we place a test charge at this point, then the electric field due to the positive charge acts away from the positive charge, and the electric field due to the negative charge acts towards the negative charge at this point. So if we superimpose these two vectors, we get the net electric field at this point. And similarly, if we place a test charge at this point, the electric field due to the positive charge points away from it, and is less intense than at this point over here, as we can see, because the test charge is further from these charges. And here the electric field due to the negative charge points towards it, so we can sum up these electric field vectors using the parallelogram rule of vector addition, and we get the net electric field at this point, which points to the right. Now given that electric field maps use vectors to depict the magnitude and direction of the electric field at many locations in a given region, electric field line diagrams can be drawn, which are simplified models of electric field maps. And they can be used to determine the relative magnitude and direction of the electric field at any position in the diagram. So for example here, the electric field line diagram is more dense where the electric field is stronger. And it's more dense between a positive and negative charge compared to this point up here, for example. And if we place a test charge at this point, we'll recall that the electrostatic force is equal to the charge by the electric field. So if the charge is positive, then the force on the charge is tangent to the electric field line at this point and points in the direction of the electric field. And if we place a negative test charge, for example, then the electric force still acts tangent to the electric field line at this point, but it acts against the electric field. The following static charges with a charge magnitude Q are positioned in a square configuration at a distance d from each other. Write an equation for the force exerted by charge 4 on charge 1. So we take our positive direction vector from charge 4, and we know that the force exerted by charge 4 on charge 1 is attractive, because these are opposite charges. So therefore, for part A, we can write the electrostatic force as 1 over 4 pi by the permittivity of free space, and that's multiplied by the product of the two charges, so that will be minus q by q, so we get a negative here, over the squared distance between the charges. And that's multiplied by the unit vector pointing in a direction from charge 4 to 1. So as we can see, the electric force points in the opposite direction to the unit vector. Now part B asks us to determine the magnitude and direction of the electric field in the middle of the square. So suppose we place a test charge in the middle here, then this test charge is going to have an equal distance to all of those charges. And the positive charges have an electric field that points away from them. So this will be the electric field due to charge 4, and this one here is due to charge 2. And charge 1 has an electric field pointing towards it, and similarly for charge 3, because they're negative charges. So therefore, these two vectors will cancel each other out, and so will these two vectors, because the charges all have the same magnitude according to the problem. So therefore the net electric field in the middle of the square is 0. And note that it's a vector. Now part C asks us to determine the magnitude and direction of the electric field midway between charge 1 and 2. So let's make room over here. So the electric field points away from charge 4 and towards charge 3 and towards charge 1 and away from charge 2. So the magnitude of the electric field due to charge 4 is smaller than that due to charge 1 and 2, because the charge is further away from this point. And similarly, the electric field due to charge 3 points in this direction and has the same magnitude as the electric field of charge 4. And now we can use a bit of trigonometry to superimpose these electric fields. So if we take this as our angle theta, and if we take our positive direction pointing to the right, so we have the electric field component in the horizontal direction is minus E4 cosine theta plus E3 cosine theta. So given that E4 is equal to E3, these cancel, and the electric field component in the horizontal direction is 0. Now in the vertical direction, and taking the positive direction as upwards, we have E1 plus E2 and minus E3 sine theta. So we're taking the vertical component of this electric field vector. And similarly for E4. So given that E1 is equal to E2, because the two charges are at the same distance from this point, we can write this as 2E1. And similarly, the magnitude of the electric field due to charge 3 and 4 is the same. So we have minus 2 E3 sine theta. And by geometry, sine theta is the opposite, which is d on 2, on the hypotenuse. So we have sine theta is d on 2 over the square root of d squared plus d on 2 squared. So if we take d out of the square root, these d's are going to cancel. And doing some algebra, you'll get sine theta is 1 on root 5. And now we can substitute for E1, E3 and sine theta. So we have EY is 2 by 1 over 4 pi by the permittivity of free space, which will factor out. And E1 is the magnitude of the charge on the square distance from this point to the charge, which is d on 2 squared. And then minus E3, so the charge magnitude is again Q, over this distance to the charge. So the squared distance is d squared plus d on 2 squared by Pythagoras' theorem. And that's multiplied by sine theta, which is 1 on root 5. And let's simplify this a bit further. So we have 1 over 2 pi epsilon naught, and we'll also factor out the charge Q, and we'll also factor out d squared. So we have the reciprocal of 1 on 4, which is 4, and minus, so in the denominator we have 1 plus 1 on 4, which is 5 on 4. So taking the reciprocal, we have 4 in the numerator and 5 root 5 in the denominator. So given that this value is positive and the horizontal electric field component is 0, then this here is also the magnitude of the net electric field at this point. And the electric field is simply E by the unit vector in the vertical direction. So as we can see, this value is positive and the net electric field points upwards. When in electrostatic equilibrium, the excess charge of a conductor is distributed on the surface of the conductor. So for example, a metal conductor consists of metallic bonds where the electrons are free to move around. So if we take a section out of this conductor, we have the electrons distributed on the outer surface to get as far away from each other as possible. So we can visualize here that the electric fields, due to these charge carriers being the electrons, will cancel each other out. And therefore the electric field inside the conductor is 0. Now at the surface of the charged conductor, the electric field is perpendicular to the surface, as we can see. And this is also true for non-spherical conductors, which we'll look at later on. Now the electric field outside an isolated sphere with a spherically symmetric charge distribution is the same as the electric field due to a point charge with the same net charge as the sphere. And this equivalent point charge is located at the center of the sphere. Now for an insulator, being glass for example, the electrons are restricted to the covalent bonds between the molecules to form this covalent network solid structure. So therefore if we transfer electrons to this insulator, they're going to get trapped in the molecular structure of the solid, given that the electrons in the covalent bonds are restricted. So under electrostatic conditions, when these charges stop moving, the excess charge of the insulator is distributed throughout the interior of the insulator, and you'll also have the excess charge residing on the surface. So therefore the electric field within the insulator may have a non-zero value. And we'll look at these different charge distributions, including charge density functions, when we go through Gauss's law. Recall that we determined the electric field for a charged object which had a negligible size in the context of the problem being analysed, and therefore we treated the object as a point charge, and where this charge was positive, the electric field points away from it and drops off according to the squared distance away from the charge. Now in problems where we cannot treat an object as a point charge, such as in the case of a wire with the charge distributed on it, and similarly a plate with the charge distributed over its area, then what we do is determine a differential charge. So for example, along this wire, and therefore we can write the differential electric field as follows. And then what we do is integrate this equation to determine the electric field due to the charges distributed on the entire body. So we have 1 over 4 pi by the permittivity of free space being constant, and then we integrate dq on r squared, effectively superimposing those differential electric fields. And the electric field points in the direction of the unit vector from a positive charge to a point in space where we're determining the electric field. Now for a charge distributed along a line, we can take the differential charge as the linear charge density, which is in coulombs per length, and then multiply by the differential length, for example along this wire, or dx, gives us a differential charge in coulombs. And similarly for this plate, we look at a differential area of charge, and we thereby take the areal charge density, which is in coulombs per area, and integrate over the area. So again our differential charge is in coulombs. And similarly for a distributed charge on a three-dimensional body, we take the charge density, which is in coulombs per unit volume, and then multiply by the volume of the differential element, gives us a differential charge in coulombs. And we'll utilize symmetry to our advantage to simplify determining the electric field for a charge distribution on different bodies. And now we'll cover some examples where we apply this integral. Let's determine the electric field for an infinitely long wire at a point along the bisector. So therefore, using this differential equation to determine the electric field, we'll integrate it. So we have 1 over 4 pi by the permittivity of free space by the integral with respect to the charge. And we multiply by the unit vector from the differential charge to that point. Now due to symmetry, we only need to analyze half of this wire. So we're going to integrate from 0 to infinity, because we can see that the electric field, due to the differential charge on one side of the bisector, is going to cancel the electric field due to the differential charge along the other side of the bisector in the horizontal direction. So basically we resolve this differential electric field in the horizontal and vertical directions. So in other words, in the horizontal direction, these vectors are going to cancel, and therefore the electric field is 0. And in the vertical direction, we're integrating over 1/2 of the wire, so we have 2 multiplied by 1 on 4 pi by the permittivity of free space, and we integrate from 0 to infinity. And remember that the linear charge density can be used to rewrite the differential charge in terms of the length of the wire, so that will be the linear charge density dx, and that's divided by r squared, which is x squared plus y squared. So this is the origin that we're taking. So we can write r squared as x squared plus y squared. And remember that the electric field was resolved in the vertical direction. So these angles here are all equal. So to get the vertical component, we multiply by cosine theta, which is y on r. So note that r is the square root of x squared plus y squared. And now we can simplify this integral as 1 over 2 pi epsilon naught. And the linear charge density and y are constant, so we're going to take them out of the integral. So we have dx on x squared plus y squared to the power of 3 on 2 in the denominator. And now we can use trig substitution to evaluate this integral. So note that tan theta is x on y, so x is y tan theta, and therefore dx is y sec squared theta d theta. So note that y is always constant, being the vertical distance from the origin to the point where we're determining the electric field. So now if we make those substitutions, we have dx is y, which we'll take out of the integral. We have sec squared theta d theta. And x squared is y squared by tan squared theta, which will factor out. So we have plus 1, and that's to the power of 3 on 2. So note that our integral was with respect to x previously. So as we can see, as x approaches infinity, this line gets flatter and flatter. So theta gets shallower and shallower and approaches pi on 2. So have a think about this. So therefore we integrate from 0 to pi on 2 when we're integrating with respect to theta. So let's keep simplifying this integral. So we have y squared to the 3 on 2, which is y cubed in a denominator. So therefore y squared on y cubed will cancel. So we get a y in the denominator. And in the numerator we have sec squared theta. And we're left with 1 plus tan squared theta. So if we recall our trig identity, and dividing this by cosine squared theta, so what we get is sec squared theta to the power of 3 on 2, which is sec cubed theta. So therefore this becomes 1 over sec theta, or cosine theta. So if we integrate this, this becomes sine theta, evaluated from 0 to pi on 2. So the integral evaluates to 1. And therefore, our electric field has a magnitude of lambda on 2 pi by the permittivity of free space by y. So remember, with a point charge, the strength of the electric field was inversely proportional to the squared distance. But now with an infinite wire, it's inversely proportional to the vertical distance from the wire. And the direction of this electric field is in the vertical direction. So recalling the symmetry of the problem. Recall the integral we derived for the electric field along the bisector of an infinite wire. But in this case we have a finite wire, which has a length L. So we integrate from x equals 0 to x equals L on 2 due to symmetry, similar to an infinite wire. So the charge on both sides result in the horizontal components of the electric field cancelling each other out. So due to symmetry, the net electric field is going to act vertically. So in the case where the length of the wire approached infinity, we had our angle theta approach pi on 2, but in our case here, our wire has a finite length. So therefore we can use trigonometry where tan theta is equal to L on 2 being the opposite edge on the adjacent edge being y. So the distance from the origin to the point where we want to find the electric field along that bisector. So taking the arctan, we obtain theta is the arctan of L on 2y. So if we evaluate this integral, it'll evaluate the sine theta from theta is 0 to the arctan of L on 2y. So therefore we're going to get the sine of an arctan. So if we suppose this here is some general value being alpha, then using trigonometry you can simplify this to alpha on the square root of 1 plus alpha squared. So therefore the magnitude of our electric field can be written as follows. So we have alpha is L on 2y over the square root of 1 plus L on 2y squared. So we can put 2y in the denominator, which gives 4y squared. And we have the charge density by the length of the wire in the numerator, which is a net charge on that wire. So effectively, if y is much larger than the length of the wire, then this term here disappears. And the square root evaluates to 1, and we end up with the finite wire behaving like a point charge. And note that the direction of this electric field points upwards due to symmetry. Let's determine the electric field of a thin ring along its axes. So here we look at the plan view to visualize our charge distribution along that ring, and we'll label this vertical distance from the origin of the ring to a point along its axis as z. And note that this problem is also symmetric, because if we take a differential charge along the ring on one side, then we'll have the same differential charge on the other side, resulting in an electric field that points in this direction. So again, if we resolve these differential electric field vectors in the horizontal and vertical direction, the net electric field in the horizontal direction is going to be 0, because these will all cancel. So therefore our net electric field is going to act in the vertical direction. So we have 1 over 4 pi epsilon naught, and we're integrating with respect to the charge. So now given the charge is distributed along a circle, then we can write the differential charge as the linear charge density by this distance over here, which is the radius of the ring, d theta. And note that because we took the electric field component in the vertical direction, we need to resolve it in the vertical direction, so we'll take this angle of theta to do that. So taking cosine theta, we get z on r. So if we substitute for dq, we can take lambda and r outside the integral because they're constant. And we can also take z outside the integral because that's going to remain constant. So we have d theta on r squared, which using Pythagoras is z squared plus r squared. And then multiplying this by r, which is a square root of z squared plus r squared, we get this expression to the 3 on 2. And here we're integrating with respect to theta. So from theta equals 0 to 2 pi, given we have a circular ring. So given z and r are constant, we can take this expression outside the integral. So therefore the integral is evaluated to theta from 0 to 2 pi. So therefore we end up with the linear charge density by 2 pi r z. And this is the magnitude of our electric field. And the resulting electric field vector points in the vertical direction. Now note that we can make some analogies with a point charge. So the linear charge density multiplied by 2 pi r is going to give the net charge on that ring in coulombs. So therefore we can rewrite the magnitude of this electric field as q by z on 4 pi by the permittivity of free space. And let me remove this, by z squared plus r squared to the 3 on 2. So therefore with the distance to the point where we're determining the electric field is much larger than the radius of this ring, then this term becomes dominant and we can ignore this second term. So we end up with E is the charge by z on 4 pi epsilon naught, and z squared to the 3 on 2 is z cubed. And z on z cubed gives z squared in the denominator. So we can see that the thin ring behaves like a point charge at large distances from it. We can also determine the electric field at the center of a charged semicircular arc using integration. So if we take a differential charge along the arc, at the center of the arc, the electric field vector points radially and towards a negatively charged element. And on the other side, we have a similar vector, which we can again resolve in the horizontal direction and the vertical direction. So there's no net electric field in the horizontal direction due to symmetry. So if we take our angle theta as follows, our net electric field is going to point in the vertical direction, and our differential charge can be taken as the linear charge density by the arc length where this differential charge is distributed. So that will be r by the differential angle d theta. So lambda and r are going to be constants, so we'll take them out of the integral. So we have d theta on r squared, where r is the distance from this point to the differential charge, which is also constant. And we want the vertical component of the electric field, so we take sine theta. So simplifying this integral, we have lambda on 4 pi epsilon naught by r on r squared, which is r, and we're integrating from an angle of 0 to half of the arc being pi on 2. And therefore we multiply the result by 2 due to the symmetry of the problem. So in other words, the electric field, due to a differential charge on this side, is going to have the same magnitude. So we have sine theta d theta. So this integral evaluates a minus cosine theta from 0 to pi on 2. So it's going to evaluate to 1. And therefore we obtain lambda on 2 pi epsilon naught r. So this is the magnitude of the electric field at the center of the semicircular arc, and due to symmetry it acts upwards. Let's determine the electric field at a collinear point that's at some distance d from the end of the wire. So if we take our x direction as follows, and our differential element of charge, we can see that the electric field is going to point to the left, so radially from the charge. So what we have is the electric field in a horizontal direction is 1 on 4 pi epsilon naught, and our integral is as follows. So in this case our differential charge is the linear charge density by dx, and our radial distance from this differential charge to this point that's collinear with the wire is x plus d. So we can rewrite this integral as follows, taking lambda outside, which is constant. So we have dx on r squared. And we're integrating from x equals 0 to the length of the wire. So here we can use u substitution. So du is dx, and therefore our integral is written as follows. So that's going to evaluate to u to the minus 1 on minus 1, or minus 1 on u. And if we substitute back for u, we can rewrite our integral as follows. As minus 1 on x plus d, evaluated from 0 to L. So what we get is lambda on 4 pi epsilon naught minus 1 on L plus d. Then minus minus is a plus 1 on d. So you multiply the cross terms and add them together and divide by the product of the denominator. So that's going to give you the following result, being the linear charge density by L on 4 pi epsilon naught d by L plus d. So if we write this as the total charge on the wire, and where the distance from the wire to this point is much larger than the length of the wire, then we can write the electric field magnitude as Q over 4 pi epsilon naught d squared, because this term will dominate compared to this one. So the finite wire acts like a point charge, with the collinear point where we're determining the electric field is far from the wire. Flux describes the amount of a given quantity that passes through a given area. So for example, if we visualize these vectors representing the velocity of different particles of fluid, then the volume of fluid that flows through this area per unit time is the area by the velocity. So this gives units of volume per second, which is the volumetric flux, or the volume of fluid that flows through this area per unit time. And if we multiply this by the density of the fluid, we get the mass flux. So density by area by velocity will be mass per volume. So for example, kilo per cubic meter by meters cubed per second, which will give units of mass per unit time, which is the mass of the fluid that flows through the area per unit time. Now if we consider these vectors to be electric field vectors, then the electric flux is defined as a dot product between the electric field vector and the area vector. So for example, for this vertical surface, we have the unit vector that's normal to this surface, pointing in this direction. So the area vector is just the area by the normal vector, where the normal vector is a unit vector. And this form of the electric flux is for the case where the electric field vector is constant across the area. So noting the dot product can be written as the product of the magnitudes of both vectors by the cosine of the angle between them. So in this first case, where the electric field and the normal vector are parallel, then you're going to get the maximum electric flux through that area, because the cosine of the angle between them, being 0, is 1, which is a maximum. Now in this case over here, where the orientation of the surface is oblique, so the normal vector and the electric field vector are not parallel in this case, then more of the electric field is going to pass through this surface compared to this one. So as we've seen, the direction of the area vector is perpendicular to the plane of the surface, and it points outwards from a closed surface. So for example, if we look at this spherical surface, then the area vector is going to point outwards from this surface. If we look at different parts of this surface, so the sign of the flux is given by the dot product of the electric field vector and the area vector. So in this case over here, the flux is positive because the electric field vector and the area vector point in the same direction. And the same for this case, because the angle between the electric field vector and the area vector is less than 90 degrees. So both vectors point in the same direction. And note that under electrostatic conditions, this electric field is static, so it's not really flowing through that surface like a fluid. Now in general, the total electric flux passing through a surface is defined by the surface integral of the electric field over the surface. So here for example, we're looking at the area vector for a differential element of area. Now in the case of a sphere, you can imagine the electric field at different points on the surface of this sphere is constant. So remember that it was equal to the charge on 4 pi by the permittivity of free space, and inversely proportional to the radial distance from the charge. So in this case it's constant, where r is the radius of the sphere. And given that this electric field is always parallel to the area vector on the surface of the sphere, then cosine theta will be 1, and we can write the dot product directly as the product of the electric field and the area of the sphere. So the area of the sphere is 4 pi r squared. So therefore the electric flux through the surface of that sphere is going to be the charge on the permittivity of free space. And we're going to look at this more closely when we look at Gauss's law, where this charge is specifically the charge enclosed within that surface. Gauss's law relates the electric flux through a Gaussian surface, which is a three-dimensional closed surface, such as a sphere or a cylinder and so on, to the charge enclosed by that surface. So recall that we showed that the electric field, due to a positive charge, has vectors that are always perpendicular to the spherical surface, and the electric field is uniform on the spherical surface, where this closed surface has a radius r, and given that the electric field is always perpendicular to the surface, then this dot product becomes just a product of the electric field by the surface area, and this is the electric flux. So the electric flux, after we cancel these terms, is equal to the charge enclosed in that surface over the permittivity of free space. And if we did the same calculation for a sphere of any radius, then a radius will always cancel. So the total electric flux through a Gaussian surface is independent of the size of the Gaussian surface, as long as the amount of the enclosed charge remains constant. And we won't prove this here, but this is true for Gaussian surfaces that are not spherical. So it may look something like this, for example. So you can visualize this as where the area becomes larger, the electric field gets weaker, and the electric field is stronger where the area is smaller. So where the surface gets closer to the charge. So these cumulative effects will result in the flux being constant. Or another way to look at this is the electric flux through this smaller surface is going to be equal to the electric flux through this larger surface. So in general, we can write the flux as follows, using a circle on the integral. So this states that the flux through a closed or Gaussian surface is equal to the enclosed charge on the permittivity of free space. So in general, we construct the Gaussian surface such that the electric field that's generated by the enclosed charge is either perpendicular or parallel to the different regions of the Gaussian surface. So we saw that for the spherical case, this resulted in a simplified surface integral, which we can evaluate using algebra. So basically we utilize symmetry to construct the Gaussian surface. And now we'll look at some example problems where we apply Gauss's law. Let's apply Gauss's law to determine the electric field due to a charge distribution on a wire. So if we take our Gaussian surface away from the ends of the wire, so we'll give it a length L and a radius of r, so we can see that the electric fields due to the neighboring charges will result in some cancellations. So effectively the net electric field will always act perpendicular to this cylinder. So if we cut out a circular section from this cylinder, the electric field acts as follows, being always perpendicular to the surface. So therefore we can now simplify our flux integral and calculate it using algebra. So we have the electric field, which is uniform on this cylindrical surface. So the area on which it's acting is 2 pi by the radius of the cylinder multiplied by the length of our cylindrical Gaussian surface. So that's equal to the enclosed charge in that surface, which is the linear charge density by the length of the cylinder. And we divide this by the permittivity of free space. So therefore the L's cancel, and the electric field is the linear charge density on 2 pi by epsilon naught by the radius of the cylinder. So similar to the longer integration method that we used previously, where we had the charge distribution on an infinite wire, we say that the electric field is inversely proportional to the vertical distance from the wire. And Gauss's law resulted in a much simpler calculation. Let's use Gauss's law to determine the electric field due to a charge distribution on a thin plate. So remember that the flux through our Gaussian surface is the integral of the dot product between the electric field and a differential area vector, which was equal to the charge enclosed by our chosen surface on the permittivity of free space. So if we take a cylindrical surface that's sufficiently away from the edges of the plate, then we see the electric field vectors due to neighboring charges cancel, and that results in a net electric field in the vertical direction. So there's no electric flux through the surface in the radial direction. The electric flux is going to be through the top and bottom of the cylinder. So let's give it a radius r, and the electric field is going to be perpendicular to this surface. So we have the electric field multiplied by the area of this surface, which is pi r squared, and we multiply by 2 because we have the electric flux through the top and bottom of the cylinder, and that's equal to the enclosed charge, which is the areal charge density multiplied by the cross-sectional area of the cylinder. So the charge is distributed over this area inside our Gaussian surface. So that will be pi r squared. And now we can cancel out pi and r squared. So our electric field, due to this uniformly charged plate, is the areal charge density on 2 by the permittivity of free space. And this is valid if we're sufficiently away from the edges of the plate, where the electric field becomes more complex, and we're close enough to the plate, where the dimensions of the plate are much larger than a distance from the plate. So under those conditions, the electric field is constant. Let's determine the electric field for a few special cases with planar symmetry. Recall that for a thin plate that's positively charged, and at some distance from the plate that's very small compared with the dimensions of the plate, we found the electric field was the areal charge density on 2 by the permittivity of free space, and that was using Gauss's law. Now suppose we have this case of 2 infinite plates that are positively charged, and the distance between these plates is quite small relative to the dimensions of the plate. So if we want the electric field at a point between those plates, well, as we can observe, the electric field vector due to the red plate points upwards, and the electric field vector due to the blue plate points downwards. So therefore the electric field at points between the plates and sufficiently away from the edges is 0. And suppose we want the electric field at a point that's above the positively charged blue plate. Well, in this case we have the electric field vectors pointing in the same direction, and we assume they're the same magnitude because this distance is still sufficiently small compared with the dimensions of the plate. So therefore, the electric field is a superposition of the electric field due to the red plate and then plus the electric field due to the blue plate. So that's effectively equal to sigma on epsilon naught. And similarly on the other side over here, you're going to get the same result. And I encourage you to actually verify this using Gauss's law. By constructing a Gaussian surface and exploiting planar symmetry. Now suppose we have this case where one of the plates is negatively charged. Well, in this case, the electric field vectors are going to point from the positive to the negatively charged plate. So between those plates, using the superposition principle, we're going to get sigma on epsilon naught, as we did for this case, but between the plates. And this configuration of plates is reminiscent with a capacitor, which we'll explore in subsequent videos. Now similarly, outside these plates, so if we look at a point outside the red plate, for example, well, as we can see, the red vector, due to the positively charged plate, points downwards, and the blue electric field vector, due to the negatively charged blue plate, points upwards. So these cancel out, and the electric field outside these plates is effectively zero. If a charge density function is given for a charge distribution, such as this one over here, which says that the charge density is a function of the radial distance from the center of the sphere, which has a radius r, then the total charge can be determined by integrating the charge density over the volume of the charge distribution. And note that this method can be applied in 1 and 2 dimensions, where the charge density function describes the charge distribution on a wire or a plate. But let's show the spherical case as an example. So if we want the total charge enclosed by a sphere at some distance r from the center, then we have the total charge is the integral of the charge density function, which is in coulombs per unit volume, over the volume of that sphere. So we can write the differential volume of this spherical shell, which has an infinitesimal thickness in the radial direction, as the surface area of the shell by its thickness. And then we're going to integrate this from naught to r. So taking the constants outside the integral, so I have 4 pi rho m on r being the radius of the sphere, and then we're integrating r cubed over r. So what we get is 4 pi rho m on r by r to the 4 on 4 evaluated from naught to r. So effectively the total charge inside this sphere with the radius of r is pi rho m on r by r to the 4, where these 4's cancelled. So now applying Gauss's law, and because the electric field is constant across that surface and always perpendicular to the surface, so we can multiply the electric field by the surface area, and that's equal to the enclosed charge inside that surface, which is given by this function. So we have pi rho m on r by r to the 4, and we divide the total enclosed charge in that surface by the permittivity of free space. So that's Gauss's law. And now if we cancel pi and divide through by 4r squared, we obtain electric field being equal to rho m on 4r epsilon naught by r squared. So this is where r is less than or equal to the radius of the sphere. So the magnitude of the electric field varies parabolically, up to R. So at this point over here, the magnitude of the electric field is rho m on 4 epsilon naught by R. Now if we take our closed Gaussian surface outside the charged spherical body, so we have another spherical Gaussian surface which has some radius r, then the total enclosed charge in this case is obtained by evaluating this integral from 0 to r. So therefore our integral will be evaluated from 0 to r, and therefore this becomes r to the 4. So our total charge is effectively pi rho m by r cubed. So given this is our spherical Gaussian surface, we still have the electric flux through that surface as the electric field by 4 pi r squared, and the charge enclosed in that surface is pi rho m r cubed. And we divide this by the permittivity of free space. So if we do some cancellations, our electric field is rho m r cubed on 4 epsilon naught by 1 on r squared, where r is greater than or equal to the radius of our charged sphere. So therefore the strength of the electric field outside this sphere drops off with r squared. So the charged spherical body behaves like a point charge. Consider the charge Q2, which is in the electric field of a charged object Q1. So recall that the electric field of charge 1 is the charge over 4 pi by the permittivity of free space by the square of some distance from the charge to a point in the electric field. Now if we place charge Q2 in the electric field of Q1 and want to move this charge from this position A to position B along a curved path, well, the infinitesimal work done by the electric force is equal to the dot product between the electric force and the infinitesimal displacement vector along that path. So this electric force always acts in a radial direction, so it points radially out from charge Q1. So if we consider this here as our direction theta, so given that the electric force acts in a radial direction, then we can rewrite this dot product as Fe dr. Now if we integrate both sides of this equation, then we get the work done by the electric force when the charge is displaced from A to B. So here we're integrating from Ra to Rb. So effectively summing up the contributions of the work done as the particle moves over those infinitesimal distances along the curve. Now the electric force acting on this charge is obtained by multiplying that charge by the electric field of charge 1. So if we substitute this into the integral, we get 1 over 4 pi epsilon naught by the product of the charges over the square of the radial distance between them, and we're integrating over r. So if we take the constants outside this integral and then evaluate this integral, we get minus 1 on r evaluated from Ra to Rb. So note that this is the work done by the electric force. So what we get is Q1 Q2 over 4 pi epsilon naught minus 1 on Rb minus 1 on Ra. So the change in electric potential energy as the particle moves from position A to B in the electric field of charge 1 is equal to the negative of the work done by the electric force. So what we get is Q1 Q2 over 4 pi by the permittivity of free space by 1 on RB minus 1 on RA. So if we write this, change in electric potential energy as the electric potential energy at B minus the electric potential energy at A. And suppose that instead we want to bring this charge from a position of infinity to position B in the electric field. So as RA goes to infinity, this term disappears, and we're going to take the electric potential energy at infinity to be 0. So therefore what we get is UEB is Q1 Q2 on 4 pi by the permittivity of free space by RB. So in general, we can write the electric potential energy between two charged objects as 1 over 4 pi by the permittivity of free space by Q1 Q2 on R. Consider a system of charges. So the total electric potential energy of the system can be determined by finding the sum of the electric potential energies of the interactions between each pair of charged objects in the system. So for example, if we assemble charge Q1 in a fixed position, and then we bring charge 2 from infinity into the electric field of charge 1 at a distance of R12 from charge 1, then the electric potential energy is Q1 Q2 on a distance between charge 1 and 2 multiplied by 1 over 4 pi by the permittivity of free space. And now we'll bring charge Q3 into the electric field of charge 1 and charge 2. So therefore we have Q1 interacting with Q3. So this is the potential energy between the two charges. And we also have Q2 interacting with Q3. And if you continue this process by bringing charge N into the electric field of the previous charges, then we have Qn interacting with Q1, and charge N also interacts with charge 2, and so on up to Qn minus 1. So this result, being the total potential energy of the system, is given by this sum. So if we suppose that we're assembling 3 charges, so n equals 3, so what we have when I equals 1, we have the sum from j equals 2 to j equals n, which is 3. So therefore we get Q1 Q2 on R12 plus Q1 Q3 on R13. And then when I equals 2, we have j equals 1 plus 2, which is 3. So we get Q2 Q3 on R23. And we stop there, because I equals 2, and we're summing up from I equals 2 to I equals 3 minus 1. So have a think about this. The following static charges with a magnitude q are positioned in a square configuration at a distance d from each other. Find the total potential energy required to assemble the charges. So recall the electric potential energy of a system of 2 charges is 1 over 4 pi by the permittivity of free space by the product of the charges on the distance between them. So to calculate the total potential energy, of our system of charges, we first bring charge 1 from infinity and hold it in place. So that requires no work to be done, assuming we're in a vacuum. And now we bring charge 2 in the electric field of charge 1. So therefore we have minus q by q. And we're bringing charge 2 from a distance of infinity to a distance d from charge 1. So we divide by the distance between the charges. And now we bring charge 3 from infinitely away into the electric field of charge 1 and 2. So charge 3, using Pythagoras' theorem, is at a distance of root 2d from charge 1. So the electric potential energy due to the interaction between charge 1 and 3 is minus q by q over root 2d. And between 2 and 3 we have plus q by q over the distance between the charges. And now we bring charge 4 from infinity into the electric field of the other 3 charges. So the potential energy due to the interaction between charge 1 and 4 is minus q by minus q, which is plus q squared over the distance between them. And similarly, between charge 4 and 2, we have minus q squared over the distance between them. And between 3 and 4, we have minus q squared on d. So these terms cancel, and these terms cancel. So we're left with the total potential energy of the system is 1 over 4 pi epsilon naught. And we have minus q squared is minus 2q squared over root 2d. So if we simplify this, we get minus q squared on 2 root 2 pi epsilon naught d. The electric potential, denoted V, describes the electric potential energy per unit charge. So therefore, this has units of joules per coulomb or volt. And remember that the electric potential energy is the work done by an external agent to bring a charge from infinity into the electric field of another charge to a distance r from this charge. So if we consider Q2 to be some test charge, then we can write the electric potential for our charge Q1 as 1 over 4 pi by the permittivity of free space by Q1 on R. Or more generally, the electric potential due to some charge Q. So this is analogous to the electric field of a charge, where we were able to calculate the electric force by dropping a test charge into the electric field, and we multiply it by the value of the electric field at that point. Now if we have multiple point charges, then we can determine the electric potential due to this system of charges using the principle of scalar superposition of the electric potential due to each of the point charges. So we can take 1 over 4 pi by the permittivity of free space outside the sum, and then sum the electric potentials due to each individual charge, from charge 1 to charge n. And we can extend this to a charge distribution. So we have the electric potential due to this charge distribution to be 1 over 4 pi by the permittivity of free space by the integral of the differential charge, and we have the radial distance to some point in the electric field of the charge distribution where we're determining the electric potential. Now keep in mind that this integral may diverge for cases where the length of this wire is infinite, because recall the assumption of the electric potential energy at infinity to be 0, which is not valid for this wire because you're going to have charge at infinity. So in that case we use the definition of work due to the electric force. So recalling that the change in potential energy is the negative of the work done by the electric force. So that was the integral of the electric force over R. So between 2 points in the electric field, we have a distance to the charge of RA and a distance to the charge RB. So noting this is negative because it's a change in potential energy. So recall the relationship between the electric force and the electric field. So we can write this as a test charge Q by the electric field, and then if we divide through by the test charge, we get the change in electric potential between 2 points in the electric field of our charge. So this here is the change in electric potential energy per unit charge when a test charge is moved between the 2 points. So therefore we can instead use this work integral instead of this integral here to calculate the electric potential due to a distribution of charges. Let's determine the electric potential due to this distribution of charges along an infinitely long wire along the bisector. So recall the assumption of our electric potential energy being 0 at infinity. So that won't be valid for this case, where the length of the wire is infinite, as you'll have a charge at infinity. So therefore integrating this differential equation will give you a solution that diverges. So have a go at actually integrating it to verify that's the case. So instead, we're going to use the work definition of the change in electric potential. So as we saw previously, that was equal to the negative of the work done by the electric force per unit charge. So we get an integral of the electric field over R. And as we've derived previously, the electric field due to this charge distribution along the bisector was obtained as follows, using the symmetry of the problem. So we have the change in electric potential between 2 points along this bisector to be the negative of the work done by the electric force per unit charge. So we have the electric field, and we're integrating over y from some point ya to yb. So if we take the constants outside the integral, which is the linear charge density on 2 pi by the permittivity of free space, this integral evaluates to the natural log of y, from ya to yb. And don't forget the negative sign. So what we have is minus lambda on 2 pi epsilon naught by the natural log of yb minus the natural log of ya. And this here is the change in electric potential between those 2 points. Now in this case, as ya approaches 1, this log term approaches 0. Therefore we can take our reference point at 1, where the electric potential at A goes to 0. So note that if ya approaches infinity, then we can see that the integral is going to diverge, because there's charge at infinity. So therefore we finally obtain the electric potential at some point along the bisector is equal to minus lambda on 2 pi epsilon naught by the natural log of y. Noting that the reference electric potential is 0 at y equals 1 in this case. Let's find the electric potential due to the charge distribution on this finite wire with a length L along the bisector. So if we take our origin at this point and we take our distance to the differential charge and to the point along the bisector as follows, we can write this integral as follows. So we have 1 over 4 pi by the permittivity of free space, and the differential charge is the linear charge density by the differential length along that wire. And by Pythagoras, r is the square root of x squared plus y squared. And here we're going to integrate from x equals 0 to half the length of the wire due to symmetry. So we'll just multiply our result by 2. And now we can apply trig substitution to do a change of variables. So if we take this as theta, then tan theta is x on y, or x is y tan theta. So dx is y sec squared theta, d theta. So what we get by taking our linear charge density outside the integral because it's constant, and 2 on 4 is 1/2, is an integral where we substitute for dx, and then x squared is y squared tan squared theta, so we can factor out y squared. So we're integrating here over theta. So if we use our trig identity and divide through by cosine squared theta, we get 1 plus tan squared theta is sec squared theta. So y squared to the half is y, so therefore y on y will cancel, and sec squared theta on sec squared theta to the half is sec theta. So we get lambda on 2 pi epsilon naught by the integral of sec theta over theta. So this integral is going to evaluate to the natural log of sec theta plus tan theta. And what we're going to do is substitute for sec theta and tan theta. So we can see that cosine theta is y on r. So sec theta is r on y. And tan theta is x on y. So therefore we have our electric potential is lambda on 2 pi epsilon naught of this integral. So we have r is the square root of x squared plus y squared plus x on y. And we're evaluating this from x equals 0 to L on 2. So we get the electric potential is lambda on 2 pi epsilon naught by the natural log of the square root of L on 2 squared plus y squared plus L on 2 on y, and minus the natural log of root y squared on y, which is 1. So the natural log of 1 is 0. So this here is our electric potential at some distance y along the bisector. So as we can see, as y goes to infinity, then this term becomes insignificant compared to this one, and this term is also insignificant compared to this one. So we practically get the natural log of root y squared on y, which is the natural log of 1, which is 0, as expected. Let's determine the electric potential of this thin ring along its axes. And to do that, we're going to use this integral. So I have 1 over 4 pi by the permittivity of free space, and our differential charge is the linear charge density by the radius of the ring multiplied by the differential angle, which we can see in the plan view here. So we can write lambda r d theta on r. And we're integrating from theta is 0 to theta equals 2 pi around that ring. And if we take our vertical distance from the center of the ring to some point where we're finding the electric potential, then we can write r as the square root of r squared plus z squared. So all of these terms are constant with respect to theta. So we can write the electric potential as lambda r on 4 pi epsilon naught by the square root of r squared plus z squared. That's multiplied by the integral over theta, which will evaluate the theta from 0 to 2 pi. So we can do some cancellations, and therefore the electric potential at some point along the axis of the ring is lambda r on 2 epsilon naught by the square root of r squared plus z squared. So as z becomes large, then we can see the electric potential goes to 0. Let's find the electric potential due to a charge distribution on this semicircular arc at the center of the arc. So in this case we have negative charges, so the differential charge will be minus the linear charge density by r by the differential angle d theta. So we can substitute in this integral for dq. And the radial distance from the differential charge to the center of the arc is constant. And due to symmetry, we can integrate from theta is 0 to theta is equal to pi on 2. And we just multiply our result by 2. And we take the constants outside the integral. So we have minus lambda on 2 pi epsilon naught. And the integral becomes theta evaluated from 0 to pi on 2. So what we get is minus lambda on 2 pi epsilon naught by pi on 2. So the electric potential is minus lambda on 4 epsilon naught, which is constant at the center of this arc. Let's find the electric potential due to a charge distribution on a finite wire at a collinear point. So this has some distance d from the end of the wire, and we take our distance to the differential charge as x. So therefore we can write the electric potential as 1 over 4 pi by the permittivity of free space by the integral from x equals 0 to the length of the wire, and the differential charge is the linear charge density by dx over the radial distance from the differential charge to this point, which is x plus d. So if we take the constants outside the integral and evaluate it using u substitution, you're going to get the natural log of x plus d evaluated from 0 to L. So what we get is lambda on 4 pi epsilon naught by the natural log of L plus d, which are positive, minus the natural log of d. Or using our rules for logarithms, we can write the electric potential as lambda on 4 pi epsilon naught by the natural log of L plus D on D, or 1 plus L on D. So as the distance from the wire goes to infinity, this term approaches 0, and then the natural log of 1 is 0, so the electric potential approaches 0, as expected. Let's find the electric potential due to a charge distribution over the area of a thin disk. So using this integral, we can write 1 over 4 pi by the permittivity of free space, and the differential charge is equal to the areal charge density multiplied by this differential area of charge, which is 2 pi by the radius of this thin ring by the thickness of the ring. So therefore we have the integral of sigma 2 pi r dr on the radial distance from the differential ring of charge to a point on the axis of the disk where we're finding the electric potential. So by Pythagoras, r is equal to the square root of z squared plus r squared. And now if we do some cancellations, so 2 on 4 is a half, and take the constants outside the integral, our integral is written as follows. And here we're integrating from r equals 0 to the radius of the disk, which will denote rd. And now using u substitution, we set u is z squared plus r squared. So therefore du is 2r dr, and we can thereby write this integral as 1/2 by the integral over u, and we have u to the 1/2. So integrating u to the minus 1/2 is going to be u to the half on 1/2, and then multiplied by this half means these terms will cancel, and we're left with u to the half. So therefore the electric potential is sigma on 2 epsilon naught, and we have z squared plus r squared to the half, evaluated from naught to the radius of the disk. So we have sigma on 2 epsilon naught by z squared plus the radius of the disk squared to the half, and then minus z squared to the half, which is z. So this here is the electric potential due to the charge distribution on that disk. Electric potential difference may also result from chemical processes that cause positive and negative charges to separate. And a good example to visualize this is galvanic cells, which behave like a battery. And galvanic cells use energy released during a thermodynamically favored reaction to generate electricity. And thermodynamically favored means the reactions occur spontaneously without any external input. So if we sum these redox half reactions, which occur in separate containers, we get a thermodynamically favored redox reaction. So at the anode, oxidation occurs. So we use the following mnemonic, An-ox, where zinc is oxidized, and oxidation means a loss of electrons using our all-rig mnemonic. And at the cathode, copper is reduced, so we use red cat to remember this. And reduction means a gain of electrons. And this results in a flow of electrons from the anode to the cathode along a wire. Now at the anode, we have an electrode in a zinc nitrate solution, and at the cathode we have a copper electrode in a copper 2 sulfate solution. So when zinc is oxidized, you have solid zinc converting to zinc ions in the solution, And when copper is reduced, you have copper ions attaching to the copper electrode. So at the anode, you have a reduction of mass, and at the cathode, we have a gain of mass on the electrode. And here we have a voltmeter to measure the voltage. Now when you have excess zinc in the solution, negatively charged ions are attracted and flow from the salt bridge to balance the charge. And at the cathode, you have a reduction of copper ions, so you get positively charged ions flowing in that solution to balance the charge. And the salt bridge completes a circuit. So you can't really have an open circuit like this, or no electrons will flow. So the salt bridge completes a circuit. The value of an electric field component in any direction at a given location is equal to the negative of the spatial rate of change of electric potential at that location. So for example, if we're looking in the x direction, then we get minus dV dx. Or in the radial direction, this will be r, or y in the vertical direction. So recall for a single point charge, the electric field has the following magnitude and points in a radial direction. So it's 1 over 4 pi by the permittivity of free space by the charge on the squared distance from the charge to a point in the electric field. And recall the electric potential due to that charge at that point is 1 over 4 pi by the permittivity of free space by the charge on the radial distance from the charge to that point in the electric field. So if we differentiate the electric potential with respect to r, we're going to get a term of minus q1r squared. So therefore this will be equal to the negative of the electric field in a radial direction. So we put a minus behind it. And recall that the change in electric potential between 2 points can be determined by integrating the dot product of the electric field and the displacement along the path connecting the points. And here we put a negative behind this integral because recall the change in electric potential is equal to the negative of the work done by the electric force per unit charge. So this is basically Q times E on Q for a test charge. And for simple cases where we have a uniform electric field, so for example, for this positively charged plate, we look at a point that's close enough to the plate and sufficiently away from the edges, then we saw the electric field was the areal charge density on 2 by the permittivity of free space. So we can determine the change in electric potential to be equal to the negative of the work done by the electric force as the charge moves from the surface of the plate to this point. So in this case, because the electric field is constant, so is the electric force. So we get Q times E times the distance is the work done by the electric force, and then we divide by Q to get the work done per unit charge. Now for this case over here, we have a positively charged plate and a negatively charged plate. The electric field will point in a vertical direction, so the change in potential between a point on a negatively charged plate and a point on a positively charged plate is equal to minus the work done by the electric force per unit charge. So that will be minus E times the distance between the plates. And recall in this case, the electric field is 0 outside the plates and has a magnitude of the areal charge density over the permittivity of free space between the plates. So it's constant in this case also. So this indicates that the electric potential at the positive plate is higher than that at a point on a negative plate. So a positive test charge would move from a higher potential to a lower potential in the direction of the electric field. As we've seen, electric field vector maps are tools that can describe the electric field of a charge or a configuration of charges, such as this dipole, and these can be used to predict the motion of charged objects in the field. Now, equipotential lines are basically lines of equal electric potential, and these are surfaces in 3D. So for example, for this point charge, recall that the electric potential was 1 over 4 pi by the permittivity of free space by the charge on a radial distance from the charge. So along this equipotential line, the electric potential is the same, because these points are at the same radial distance from the charge. So equipotential lines are also referred to as isolines of electric potential. So as we can see, these isolines are perpendicular to the electric field vectors, and they can also describe the electric field. So where the isolines are condensed, the electric field is stronger, and where they're less dense, the electric field is weaker, as we can see. So recalling, the electric field had the following magnitude. So 1 over 4 pi epsilon naught by Q1R squared. So here we can see an isoline map of electric potential constructed from the electric field vector map. And conversely, an electric field map can also be constructed from an isoline map. So as we mentioned, the electric field is stronger where the isolines are more dense. And we can see that the vectors are also perpendicular to the isolines. So from this relationship, recall that the electric field was a negative of the first derivative of the electric potential with respect to the direction being considered. So given that there's no component of the electric field along an isoline, so for example, E tangent along the isoline is 0, so therefore we have minus the rate of change of the potential with respect to the tangent direction being 0, meaning that the electric potential is constant along an isoline. Now if we look at a special isoline in the middle, so in this case we have a radial vector to some point on this line being equal in magnitude to the radial vector to the negative charge. So this is true for all points on this line. So therefore, if we sum the electric potential due to both of these charges, and for a dipole, these charges have an equal magnitude but an opposite charge, so we have 1 over 4 pi epsilon naught by the positive charge on a radial distance to this point, and then minus q being a negative charge on r minus. And if we're given the magnitude of the radial vectors is equal, then v equals 0 all along this isoline. And again, the electric field has no component in the direction along the isoline. So don't confuse direction. So for example, the electric field in the horizontal direction is minus dV dx. So the electric potential does vary in the horizontal direction, but it's constant along an isoline. The following static charges with a magnitude q are positioned in a square configuration at a distance d from each other. Sketch an equipotential line along which the electric potential is 0. So recall the electric potential due to these charges is 1 over 4 pi epsilon naught multiplied by the negative charge on a radial distance to some point in the electric field, then plus the positive charge on a radial distance to that same point, and then plus a third charge on its distance to that point, and then minus Q on R4. So if we choose a point in the middle, intuitively, then we can see that the radial distances from the positive charges to that point are equal to the radial distances of the negative charges to that point. So therefore R1 is equal to R2 and R3 is equal to R4. So consequently these terms will cancel each other out. Now if we chose this point, then the positive charges will have the same radial distances to that point, and so will the negative charges. So therefore these terms will no longer cancel. So that rules out the equipotential line being vertical. Now if we choose a point between charge 3 and 4, then we can see that charge 3 has the same distance as charge 4 to that point. And similarly, charge 2 and 1 have the same radial distance to that point. So the equipotential line is horizontal and between charge 1 and 2 and charge 3 and 4, where the electric potential is 0 all along that line. When a charged object moves between two locations with different electric potentials, the change in the electric potential energy between those 2 points is the charge of the object, which is our test charge, multiplied by the change in electric potential between the 2 points. So suppose we have our test charge Q, which is moved from infinity into the electric field of charge 1 and 2. And suppose it's moved to this point first, which we denote A. So the electric potential due to those charges at point A is 1 over 4 pi by the permittivity of free space multiplied by the charge on the distance from the charge to this point. So here it'll be D on 2. So Q1 on D on 2 is 2Q1 on D. And plus the charge Q2 over that distance, which is D on 2, which is the same thing as 2Q2 on D. And now suppose this test charge moves to this point B in the electric field. So the electric potential at that point is going to be 1 over 4 pi by the permittivity of free space multiplied by Q1 on the distance to that point plus Q2 on D. So therefore delta V is the potential at B minus the electric potential at A. So that will be 1 over 4 pi epsilon naught. And Q1 minus 2Q1 will give minus Q1 on D. And we have minus Q2 on D. And from this, we can calculate the change in electric potential energy by multiplying the change in electric potential by the test charge. So this here is the change in electric potential energy. And by the conservation of energy, that's equal to the negative of the change in kinetic energy. So recall that between 2 points, we have the kinetic energy plus the potential energy at one point is equal to the kinetic energy plus the potential energy at the other point. So therefore if you subtract Ka and subtract Ub, you're going to get the change in potential energy is minus the change in kinetic energy. So the movement of a charged object between 2 points with different electric potentials results in a change in kinetic energy of the object. And this is consistent with the conservation of energy. The following static charges with a magnitude q are positioned in a square configuration at a distance d from each other. Find the speed of a test charge plus q placed at the center of the square when it reaches the midpoint between charge 1 and 4. We'll recall by the conservation of energy the change in kinetic energy will be the negative of the change in electric potential energy. And we can further write this as the magnitude of the test charge, which is plus q, by the change in electric potential as the charge moves from point A to B. And I encourage you to verify that the electric field is actually pointing upwards at this point, in the direction of the net force. So the change in electric potential is the electric potential at B minus the electric potential at A. So now writing the electric potential at A, using the superposition principle, we have 1 over 4 pi by the permittivity of free space, and the electric potential due to charge 1 is going to be minus q over the distance from charge 1 to point A, which will denote dA. And then plus the electric potential due to charge 2. So that would again be q on dA, which is the same distance to that point. And similarly, plus q on dA, being the electric potential due to charge 3. And minus q on dA for charge 4. So as expected, the electric potential at A is 0. Now the electric potential at B is 1 over 4 pi by the permittivity of free space. And then due to charge 1, we have minus q over d on 2. And the electric potential due to charge 2 is going to be plus q over the distance from this charge to point B. And similarly, charge 3 is going to give the same result. And charge 4 is going to contribute the same electric potential as charge 1. So if we simplify this by factoring out 2q, we end up with q over 2 pi epsilon naught by 1 on dB minus 1 on d on 2. So using Pythagoras, this distance to B is going to be the square root of d squared plus d on 2 squared, which is the square root of 5d squared on 4, or d on 2 by the square root of 5. So if we substitute for dB, we get 2 on d root 5. And if we multiply this by root 5 on root 5, and factor out 2 on d, we get q on pi epsilon naught d by 1 minus root 5 on root 5. And now we can substitute this into this expression, where the change in kinetic energy is equal to minus q by Vb. So that would give q squared on pi epsilon naught d, and to take out this negative sign, we just flip these two terms. So root 5 on root 5 is 1, minus 1 on root 5. So this is greater than 0, as expected for the change in kinetic energy. And given we're asked to find the speed of the charge, you can substitute 1/2 by the mass of the charge by the speed squared, assuming the charge started from rest. So finally the speed is equal to 2q squared on pi m epsilon naught d multiplied by 1 minus 1 on root 5, and we take the square root. Today we'll look at the electric fields of conductors, and recall that in a conductor you have the valence electrons detaching from the core of an atom, and they move around quite freely, whereas with an insulator the electrons are not free to move around. So this conductor is initially in electrostatic equilibrium, and as you can imagine all the charges cancel, because if you had some excess charge you're going to get a shock if you touch that metal. Now suppose we charge this conductor, such as by induction or grounding. These electrons are going to want to get away from each other as far as possible. So what happens is that the excess electrons spread out and they reside on the outer surface of the conductor, as shown here. So the mutual repulsion of all the charges on the surface of the conductor eventually creates a state of electrostatic equilibrium, which is reached quite quickly. And for uniform shapes like spheres and cylinders and planes, you're going to have a uniform charge density and an absence of an electric field inside the conductor. So if we suppose this here is our conductor and it has a thick surface, so it's a thick shell with a cavity inside, well, inside the body of that conductor and inside the cavity, the electric field is zero. So as you can imagine, the electric fields due to each of those charges are going to cancel each other out. And in non-uniform shapes, you'll also have an absence of an electric field inside a conductor. And this is best visualized if we apply an electric field outside the conductor. So in this case, we're going to choose a uniformly charged infinite plate that's much larger than the distance between the plate and the conductor. So if we choose a point in the middle of the conductor, well, this electric field is going to be uniform. So remember that it's going to be sigma on 2 epsilon naught, where this plate is sufficiently close to the conductor and sufficiently larger. So what we're going to have is an electric field vector that looks something like this. Now, in the presence of this positively charged plate, more electrons are going to be drawn towards that positive charge. So that's going to leave a positively charged region on the other side of the surface, and therefore this imbalance of charge is going to result in an electric field that's going to act in this direction. So at this particular point, you're going to have the positive charges have an electric field that points away from the positive charge, and the negative charges will have an electric field that's in the direction towards those negative charges. And if you sum up all the electric fields due to these charges, you're going to have a resultant that acts in this manner. So therefore you're going to have the electric field due to a superposition of all these charges, cancelling the electric field due to this positively charged plate, and thereby an absence of an electric field inside the conductor. And as a consequence of electrostatic conditions, well, you're going to have the electric fields due to these charges in a tangent direction to the surface, cancelling each other out. So as a consequence of electrostatic equilibrium on the surface of the conductor, you're going to have these electric field vectors from that external electric field being perpendicular to the surface. So for example, if we draw an electric field line from here, it's going to bend like this, such that the electric field vectors are going to be perpendicular to that surface. And another one that comes from here will look something like this. And on the other side, you're going to have it again being perpendicular and bend away from the conductor. Okay, so that's what the electric field is going to look like, with perpendicular components to the surface of the conductor, as a consequence of electrostatic equilibrium on the surface. So another electric field line is going to look something like this, and in the middle it'll look something like this. And you get the idea. Now that we've established that the electric field inside the body of a conductor and inside the cavity is zero, then the work required to move a charge between 2 points inside the conductor is also zero. So remember that the electric field is minus the derivative of the electric potential with respect to the direction. So if we choose some surface inside this conductor that looks something like this, well, because the electric field is zero throughout the conductor, so if I wanted to move a charge between 2 points on this surface, then the change in potential with respect to that direction is zero. And consequently, any surface within the conductor is an equipotential surface, or a surface of equal potential, because this gives the potential is constant. So even in the presence of an external electric field, this condition holds, because recall previously, we found that when I have an electric field line that's close to the conductor, it's going to bend near the surface of the conductor to maintain electrostatic conditions on the surface of the conductor. Okay, so the electric field line is always perpendicular to the surface of the conductor. Today we'll look at the polarization of conductors. So suppose we rub the glass rod here with a silk cloth, so we strip off some electrons and we're left with a positive charge. And if we bring this near a conductor, well, that's going to polarize it. So it's going to pull electrons towards that rod and leave a region of positive charge on the other side. So this is really a consequence of the conductor remaining an equipotential in the presence of an external electric field. So recall that the electric field is zero inside the conductor, and therefore these charges are going to get away from each other as far as possible. So consequently, that's going to create a dipole, and consequently a neutral conductor can still be attracted by the charge object. We've seen that a conductor shields an external electric field. So basically the external electric field bends to be perpendicular to the conductor's surface, and the conductor effectively acts as a Faraday cage with a zero electric field inside it. And this here is known as electrostatic shielding, where the electric field is shielded from entering the conductor. So electrostatic shielding can also be visualized by having an electric field due to a charge inside the conductor. So imagine that these are two conductors that are concentric with each other, and this is a section through both conductors. So the electric field due to this point charge is going to be radial, but bend to be perpendicular to the surface of the conductor. Okay, so it's going to look something like this. So it's more condensed near the charge. And this must be the case because there must be no electric field inside the body of each conductor. So given that there's no electric field inside the body of a conductor, then the electrons are going to develop on the surface of that conductor to prevent that electric field from entering the body of the conductor. So therefore, if you can imagine constructing a Gaussian surface through the body of the conductor, so this is a spherical surface, then the net charge inside that Gaussian surface is zero. So remember that the electric flux is the closed integral over that surface, and we integrate the dot product between the electric field vector and the area vector, and that's equal to the total charge enclosed in that surface on the permittivity of free space. So therefore the charge due to those electrons on the surface of the conductor is going to cancel out the positive charge, and therefore the net enclosed charge in that surface is going to be zero. So therefore the flux through that surface is also zero. and there's no electric field in the body of the conductor. Now, due to electrons developing on the bottom surface of that conductor, so that's going to leave behind positive charges on the other surface of the conductor. And physically, the deficiency of electrons on that surface is modeled by positive charges. So therefore, this conductor is going to act like a point charge, producing an electric field that emanates radially from it. So all around that surface. And consequently, electrons are going to be attracted to that positive charge. So you're going to have on the inner surface of the other conductor a bunch of electrons that are going to shield the body of that conductor from an electric field. So remember that the electric field inside a conductor is zero. And consequently, when you have those electrons developing on the bottom surface, they're going to leave behind positive charge on the other surface. So the net charge on this outer surface is plus Q, which is equal to this charge. And the net charge on the inner surface of this conductor is minus Q. And then plus Q, minus Q, plus Q. Because if you construct the Gaussian surface in the middle of that conductor, you have a charge of plus Q, minus Q, plus Q, minus Q. So the electric field inside the body of the conductor is zero. And that's the most important idea. Consider two concentric spherical thick shell conductors. The inner shell carries an excess charge of plus Q, and the outer shell carries an excess charge of plus 2Q. And we're asked to find the electric field for the following cases. So a conductor carries its excess charge on the outer surface under electrostatic equilibrium conditions. So therefore, the electric field inside the inner shell of this conductor is zero, and the electric field inside the body of the conductor is also zero. Now the electric field between the outer shell of this conductor and the inner shell of this conductor can be obtained by constructing a Gaussian surface that's at a distance r from the center. So if you applied Gauss's law, you'd obtain the electric field is 1 over 4 pi by the permittivity of free space by Q on r squared. Now because you have a positive charge on the outer surface of this inner conductor, then electrons are going to build up on the inner surface of the outer conductor, effectively shielding its body from this electric field. So therefore, if you construct a Gaussian surface inside the body of this conductor, the net charge inside that surface is zero. So therefore the electric field in the body of the conductor is zero. Because the net charge, due to the buildup of these electrons, is minus Q. And therefore at the outer surface of the conductor, you're going to have a deficiency of electrons. So you're going to have a net positive charge built up on the outer surface of the conductor. So that would also be plus Q. So therefore the net positive charge on the outer surface of the conductor is plus 3Q. And now if you construct a Gaussian surface outside this conductor at some distance r from the center, then you'll find that the net enclosed charge is plus Q minus Q is 0, plus 3Q. So therefore the electric field is 1 over 4 pi by the permittivity of free space by 3Q on r squared outside this conductor. So you can see that at points outside the conductors, The conductor acts like a point charge that's focused at its center. A solid spherical conductor with a radius r carries an excess charge q. So this charge is carried on the surface of the conductor. Sketch the variation of the electric field and potential as a function of the distance r from the center of the sphere. While inside the body of the conductor, the electric field is 0, which you can verify by constructing a Gaussian surface. And then constructing a Gaussian surface outside the sphere, you'll find that the electric field is 1 over 4 pi by the permittivity of free space by the charge q on r squared. So that's for r greater than or equal to r, and therefore at r equals the radius of the sphere, we have the electric field is 1 over 4 pi epsilon naught by q on r squared, and it varies with the inverse of the squared distance from the center of the sphere. Now the electric potential inside the sphere is constant and equal to 1 over 4 pi epsilon naught by q on the radius of the sphere. So remember, the electric field is 0 inside the sphere. So that's for r is less than r. And thereafter, the electric potential is 1 over 4 pi by the permittivity of free space by q on r. So it varies with the inverse of the distance from the center of the sphere. A spherical conducting shell with a radius Ra carries a charge plus q and is suspended from another conducting spherical shell which has a radius Rb and carries a charge of minus 2q. So remember that the excess charge is distributed on the surface of the conductor. Now what is the electric potential inside the inner conductor? Well, we know that the electric field inside a conductor is 0 if there's no charge inside that conductor. So therefore the electric potential is constant. So all we need to do is find the electric potential at the surface of the conductor, and we have the electric potential at any point inside the conductor. So the change in electric potential is minus the work done by the electric force as some test charge moves from infinity to a point on the surface of the inner shell. So we can break this up as minus the work done as the charge is moved from infinity to a point on the outer shell, minus the work done as the charge is moved from B to a point on the inner shell. And this is divided by the test charge. So minus the work done by the electric force from infinity to B on the test charge is the electric potential at B. And we have minus 1 on Qt by the integral of the electric force, which is a test charge by the electric field, integrated over R. And we're integrating from the radius Rb to Ra. So therefore the test charge cancels, and we can write this as the electric potential at B minus, and the electric field is due to the charge inside the conductor. So that would be Q on 4 pi by the permittivity of free space by 1 on R squared. So we took the constants outside the integral. And now if we evaluate this integral, you'll get the potential at B minus Q on 4 pi epsilon naught, and we get minus 1 on R evaluated from RB to RA. So therefore the minus sign cancels, and we know that this spherical shell, by Gauss's law, acts like a point charge concentrated at the center. So therefore the electric potential at B is 1 over 4 pi epsilon naught, and that's multiplied by the net charge, which is Q, minus 2Q on RB. So if we substitute into here, we get 1 over 4 pi epsilon naught by minus Q on RB, and then plus 1 over 4 pi epsilon naught by Q on RA minus Q on RB. And note that this is the change in electric potential as the charge was moved from infinity to the surface of the inner shell. And the electric potential at infinity is 0. So therefore we get VA is 1 over 4 pi epsilon naught, and then we have Q on RA minus 2Q on RB. Which is the electric potential at any point inside the inner conductor. Given the electric field for a long conducting cylindrical wire, which has a radius r and a uniformly distributed positive charge, find the electric potential at a distance r from the center of the wire relative to the surface of the wire. So we want the change in electric potential from r, being the radius of the cylinder, to some distance r above the wire. So that will be minus the work done by the electric force as we move the charge from R to R. And that's divided by the test charge, which is equal to minus the integral of the electric force, which is the test charge, by the electric field, integrated over R, from the radius of the cylinder to some distance above the center of the cylinder. And that's divided by the test charge, so we can get rid of it from the integral. So we have minus the integral of the given electric field, which is the linear charge density on 2 pi by the permittivity of free space by R integrated over R. So taking the constant outside the integral, we have minus lambda on 2 pi epsilon naught, and evaluating this integral gives the natural log of R, evaluated from capital R to small r. So therefore the change in electric potential between those 2 points is minus lambda on 2 pi epsilon naught by the natural log of R minus the natural log of the radius of the cylinder. So this is the same as minus the natural log of R plus the natural log of R. So if we apply our rules for logarithms, we get the change in electric potential between those 2 points is lambda on 2 pi epsilon naught by the natural log of r on r. Consider two conductors that are charged, so the larger conductor has some electric potential and the smaller conductor also has an electric potential. And note that each sphere is an equipotential surface, because the excess charge is distributed on the surface of the conductor. Now suppose we place these two conductors in electrical contact, so we have a long wire connecting the two, and therefore the charge carriers, being the electrons, will move between the conductors such that the surfaces of each conductor are at the same electric potential. So remember, it's the electrons that flow through this wire which are the charge carriers. So when this happens, this conductor will have a higher net positive charge and this conductor will have a lower net positive charge. And we consider these conductors to be sufficiently far away that their electric fields do not affect each other. So therefore the electric potential of the larger conductor is 1 over 4 pi epsilon naught by the excess charge on the larger conductor on its radius. So under electrostatic conditions, these conductors have the same potential, so therefore this is equal to 1 over 4 pi epsilon naught by the excess charge on a small conductor over the radius of the smaller conductor. So these cancel, and therefore if we multiply through by the radius of the smaller sphere, we have Rs on Rl, and then divide through by the charge on a larger sphere. So we have Qs on Ql. And we know the electric field of the larger conductor is 1 over 4 pi by the permittivity of free space, and we have Ql on Rl squared. And similarly for the smaller conductor, we have 1 over 4 pi epsilon naught by Qs on Rs squared. And now if we take the ratio of the smaller electric field to the larger one, then these terms cancel and we get Qs on Rs squared divided by Ql on Rl squared, which is the same as Rl squared on Ql. And remember that Qs on Ql was equal to Rs on Rl by our condition that the electric potential of both conductors is the same. So what we get is Rs on Rl. So doing some cancellations, we get Rl on Rs. So therefore if we multiply through by the electric field of the larger charge, we get the electric field of the smaller charge is Rl on Rs by El. And therefore, given that the radius of the larger sphere is larger than that of the smaller sphere, the electric field of the smaller sphere is stronger than that of the larger sphere. So the radius of curvature of the smaller sphere is smaller than that of the larger sphere, and therefore the curvature of the smaller sphere is the reciprocal of the radius of curvature is higher than that than the curvature of the larger sphere. So this suggests that if we have an irregular conductor, then the charge density on the surface of this conductor will be higher where there are points or sharp edges compared to smooth edges. So on the surface of this conductor, we'll have a higher charge density in this region compared to the charge density on this smoother edge. So the basic idea is that the charges are distributed in this way such that the conductor remains an equipotential surface regardless of its shape. So the electric field inside the conductor is still zero. So remember that if you have an external electric field due to this conductor, for example, then the electric field lines are going to bend to be perpendicular to the surface of this conductor. So they'll look something like this. So they point out radially from this conductor, and then they bend as follows. To maintain electrostatic conditions on the surface of the conductor. Ground is an idealized reference point that has zero electric potential. So it can absorb or provide an infinite amount of charge without changing its electric potential. Now we can induce charge on a conductor by grounding it in the presence of an external electric field. So for example, if you have this rubber rod rubbed with fur, then electrons get attached to the rod and it becomes negatively charged. And if we bring it near a conductor, then it's going to repel electrons away from it. And now if we attach a wire from the conductor to the ground, then these electrons will want to get further away. So they escape the conductor. So effectively, the conductor now has a net positive charge. So therefore, when we cut this wire and then move this rubber rod away from the conductor, the electrons will have no way of getting back, and the surface of the conductor carries a net positive charge. A capacitor stores charge. And the first example we'll look at being a parallel plate capacitor, which will represent in a circuit as two straight lines with a gap in between. So suppose we connect a battery using a wire to both sides of the capacitor, so the anode of the battery repels electrons. So these get stored on the bottom plate of this capacitor. So remember that when we connect two conductors, being one of the plates of this capacitor, to the anode of the battery, then the charges are going to get distributed such that they're both at an equal potential. So the battery has a voltage, being a potential difference. So we have V minus at the anode and a potential of V plus at the cathode. So in a similar way, when the cathode is connected to the top plate, then that's going to attract electrons. So again, the charge is distributed such that the cathode and the top plate are at the same potential. And therefore, this top plate now has a deficiency of electrons. So we model that as positive charges. So therefore, once the potential difference between these plates reaches that of the battery, then the electrons effectively stop flowing. And the capacitor has stored charge on the top and bottom plates. So effectively, these result in an electric field between the two plates. Now the capacitance of this capacitor relates the magnitude of the charge stored on each plate, which is going to be equal to the electric potential difference that's created due to the separation of these charges. Now while in most textbooks this potential difference is referred to as the work done to separate those charges, the electrons are not really jumping from plate to plate because there's no pathway for them to do that. So that's something to keep in mind by thinking about the physics to how the capacitor gets charged. Now the unit of capacitance is coulombs per volt. So the potential difference between 2 points, particularly the positive and negative terminal of a battery, is the voltage. And 1 coulomb per volt is 1 farad, which is named after Faraday. Now the capacitance of a capacitor depends only on the physical properties of the capacitor. And one of those properties is the shape. So for example, you may have parallel plates, as we've seen, concentric spherical shells, or coaxial cylinders. So this is referred to as a coaxial cable. And the material used to separate the plates. And this will become more clear when we look at dielectrics, or insulating material placed between the plates of the capacitor to increase the capacitance. And the main idea is that both shells or cylinders store an equal amount of charge. So remember that excess charge is stored on the surface of a conductor. And I'm specifically looking at a parallel plate capacitor. The capacitance of a parallel plate capacitor is proportional to the area of one of its plates and inversely proportional to the distance between the plates. And the constant of proportionality is the dielectric constant, represented as kappa. So this depends on the insulating material placed between the plates, and that's multiplied by the permittivity of free space. And that constant of proportionality is multiplied by the area of one of the plates and divided by the distance between the plates. So note that these parallel plates are basically surfaces. So for a given voltage, a higher capacitance means that more charge can be stored on the plates. And here we can see the capacitance increases with the area of the plate. So a larger area means more charge can be stored. And the capacitance decreases with an increasing distance between the plates. So this is because when the distance between the plates increases, then the electric field between the plates becomes weaker, and that reduces the ability of the capacitor to store charge. And this will become clear when we derive this relationship from the electric field. Recall that the electric field between two parallel charged plates with a uniformly distributed electric charge, so for example in our parallel plate capacitor, is constant in both magnitude and direction, except near the edges of the plates. So note that these plates are planar surfaces, and the charge is distributed over their area. And remember that we've used Gauss's law and the principle of superposition to determine the magnitude of the electric field between the two plates, where the separation between the plates is much smaller than the dimensions of the plates. So this will be the case for our parallel plate capacitor. And that was equal to the areal charge density on the permittivity of free space. And you can verify this, for example, by constructing a Gaussian surface around one of the plates. So this can be a closed cube or cylinder. So have a go at doing that yourself to verify this. Now remember that the capacitance of a capacitor was equal to the charge on the voltage, which is a change in electric potential between the two plates. And remember that we found the change in electric potential as we move the positive charge from the positively charged plate to the negative plate as minus the electric field by the distance between the plates. Now we can make an analogy that the work done to separate the charges is attributed to moving an electron from the positively charged plate to the negatively charged plate. So in this case, the electric force would point downwards and do negative work. So in this case, the change in electric potential between the positive and negative plate is E multiplied by D. So note that this is only an analogy, because with a parallel plate capacitor, the electrons are not really jumping from plate to plate, as we saw previously. Now the charge density is the charge on one of the plates per unit area. So therefore we can write the electric potential as the charge on one of the plates over the area of one of the plates by the permittivity of free space multiplied by the distance between the plates. And therefore if we substitute this into the capacitance equation, then what we get is Q over delta V. So that will be the same thing as Q by A epsilon naught over QD. And if we cancel out the charge, we can write the capacitance as the permittivity of free space by the area of the plate over the distance between the plates. And when we look at dielectrics, we'll see that inserting an insulating material between the plates will further increase the capacitance. So we multiply this by the dielectric constant for that case. Recall that the capacitance is equal to the charge stored on the plates of the capacitor for a given voltage. So therefore, the charge is proportional to the voltage. So it has a linear relationship with the slope being equal to the capacitance. Now remember that we found the electric potential as the work done by an external agent to separate the amount of charge on the capacitor. And we assume that an electron jumped from the positively charged plate to the negatively charged plate. So that's how it's presented in textbooks, but it's not what physically happens, as we saw in our analogy of how conductors behave when they're connected together. So remember that the change in electric potential energy was equal to some charge by the change in electric potential. So in our case for the capacitor, the initial energy stored in the capacitor is 0. And as it gets charged, we see that the charge increases linearly with the voltage, or change in electric potential between the two plates. So therefore the average voltage from when we start to charge a capacitor to when it's fully charged is 1/2 delta V, and then multiplying it by the charge stored on one of the plates of the capacitor gives the electric potential energy stored in the capacitor. So note that this is equal to the change in electric potential energy stored in the capacitor, because as we saw, the capacitor is not initially charged. And that's why you have this half here. So the electric potential energy stored in the capacitor is equal to the area of this triangle. So given this relationship, we can write the electric potential energy stored in a capacitor as 1/2 by the capacitance by the voltage squared, or alternatively, if we write the voltage as the charge stored in the capacitor on the capacitance, then this can also be written as Q squared on 2 by the capacitance. Let's find the capacitance of a capacitor with 2 concentric spherical shells, where the inner shell has a radius Ra and the outer has a radius Rb, and the inner shell carries a charge of plus Q and the outer shell minus Q. So remember, the capacitance is equal to the charge stored on one of these shells on the change in electric potential between those two shells, or the voltage. So remember that if you construct a Gaussian surface outside this outer shell, then a net enclosed charge is 0, so there's no electric field outside these shells. So remember that the change in electric potential is equal to the negative of the work done by the electric force per unit charge. So we can take this as the negative of the integral of the electric field over R. And suppose we're moving a test charge from infinity to some point between these shells. Well, there's no work required to move that test charge from infinity to a point on the outer shell, given the electric field is 0. So therefore the work done is attributed to moving the charge from Rb to Ra. And if you construct a Gaussian surface between these shells, you'd see the electric field is attributed to the enclosed charge, which is the charge on the inner shell. So what we have is minus the integral from Rb to Ra, and that's multiplied by 1 over 4 pi by the permittivity of free space by the charge Q on R squared. And we're integrating over R. So what we get is minus the charge over 4 pi epsilon naught. And evaluating the integral, we get minus 1 on R, evaluated from Rb to Ra. So therefore the voltage is equal to Q on 4 pi epsilon naught. And here we'd get minus 1 on Ra minus 1 on Rb. And then taking the minus of that gives you 1 on Ra minus 1 on Rb. And then doing a bit of algebra, you'd get Q on 4 pi epsilon naught. And we multiply the cross terms, so we get Rb minus Ra on Ra Rb. So if you substitute this into the capacitance equation, you'd get Q on 4 pi epsilon naught. So the Q's cancel, and you get 4 pi epsilon naught in the numerator. And then you'd get Ra Rb in the numerator over Rb minus Ra. And that's the capacitance of our spherical capacitor. Let's find the capacitance of a capacitor consisting of two coaxial cylinders. So remember the electric field of a cylindrical wire or cylindrical conductor was the linear charge density on 2 pi by the permittivity of free space by the distance from the center of the wire. And this type of capacitor is also known as a coaxial cable. So if the inner cylinder has a positive linear charge density and the outer cylinder has a negative linear charge density, then if you construct a Gaussian surface that's cylindrical outside the cable, then you're going to have the net charge enclosed in that surface being 0. So the electric field outside the capacitor is 0. So therefore the change in electric potential, being the change in electric potential energy per unit charge, is minus the work done by the electric force per unit charge. So we can write this as minus the integral of the electric field over R. And what we're doing is moving the test charge from some point on this cylinder. So we'll give this an outer radius RO to a point on the inner cylinder. So we'll call this radius Ri. So taking the constants outside the integral, and evaluating the integral, we have the natural log of R evaluated from RO to Ri. So that will be equal to minus lambda on 2 pi epsilon naught by the natural log of Ri minus the natural log of the outer radius. And we can take the negative sign inside the parenthesis, so you'd get a plus and a minus here. And therefore the voltage of our capacitor is lambda on 2 pi epsilon naught by the natural log of the outer radius on the inner radius. So recall that the capacitance is the charge on the voltage, and remember the charge is simply the charge density by the length of the cable. So if you substitute for the voltage, what you'd get is lambda in the denominator and 2 pi epsilon naught in the numerator, and the natural log would go in the denominator. So the charge density cancels, and we'll make a bit of room here. So therefore the capacitance is 2 pi epsilon naught by the length of the cable on the natural log of the radius of the outer cylinder on the radius of the inner cylinder. So note that this here is a solid conducting cylinder, and this cylinder is the outer shell. And these would have an insulating material between them to prevent them from touching in reality. A proton with a mass mp and charge E is fired between two parallel charged square plates of a capacitor as shown. Now the plates have a length L and a separation D, and we can assume gravity is negligible. Now part A asks to draw the electric field and force vectors when the proton is halfway along the plates as shown. So we have our length L and separation d. Well, in this case, the proton is being deflected upwards, and because it's a positive charge, is deflected in a direction of the electric field. So therefore the electric field and electric force vectors point upwards. Now in part B, we're asked to write the strength of the electric field in terms of the mass of the proton, the length of the plates, the separation between them, and the initial speed of the proton. Well, we know that the charge by the electric field is the electric force, and that's equal to the mass of the proton by its acceleration. And the proton is deflected like a projectile, so if we take our initial y position as 0, and our final y position as a separation between the plates on 2, then using the kinematic equation, we have the final position as d on 2 is equal to the initial y position plus the initial velocity component in the vertical direction, which is 0, multiplied by time, and then plus 1/2 by the acceleration, which is the charge by the electric field on the mass of the proton, by t squared. And given there's no horizontal forces on this charge, then in the horizontal direction we have the final x position is equal to the initial position x0 plus the initial velocity in the horizontal direction by time. So we get t is L on V0. So if we substitute for t, we get L squared on V0 squared, and then cancelling out the 2, and these are 0, we can solve for E. So the strength of the electric field is the mass of the proton by d by the initial speed squared over the charge of the proton by the length of the plate squared. Now part C asks for the charge on the bottom plate. So recall the electric field was equal to the areal charge density on the permittivity of free space. So that will be the charge per area of the plate, which is L squared for the square plate by epsilon naught. And then if you substitute this into this expression, you'll obtain Q on L squared epsilon naught is the mass of the proton by the separation between the plates by V0 squared on EL squared. And if you multiply through by L squared, these cancel, and then multiplying through by epsilon naught, you'll get the charge on the bottom plate. So that's part C. And in part D, we're asked to find the potential energy stored in the capacitor. So that's UC is 1/2 by the charge by the voltage. And remember that the voltage was equal to the negative of the work done by the electric force to move an electron from the bottom plate to the top plate per unit charge. So that was minus the electric field by the separation between the plates. So therefore the change in electric potential is E times D. So I'll leave it for you to substitute for the strength of the electric field into this expression, and then substitute this along with the charge to obtain an expression for the potential energy stored in a capacitor. A dielectric is an insulating material that's used in different electrical components, such as resistors, capacitors, and so on. But here we'll focus on their application in capacitors, as we'll look at resistors later on. So recall that when we connected a parallel plate capacitor to a battery, the anode is going to result in electrons being drawn towards the bottom plate of the capacitor. So they're collected on the bottom plate, and the cathode is going to draw electrons away from the top plate, leaving behind a region of positive charge. And this continues until the voltage or change in electric potential is equal to that of the power source. So therefore, the difference of charge results in an electric field between those plates. Now suppose we remove the power supply, and therefore the charge on those plates is going to remain constant under this condition. And suppose we insert a dielectric between the plates of the capacitor. So given that electrons are not free to move in this insulating material, the material is going to become polarized due to the presence of this external electric field, which we'll call E0, without the dielectric inserted. So we can model this as follows, with the electrons being polarized towards a positively charged plate and vice versa. So let's just draw a few of those in. So this results in an electric field that opposes this external electric field produced by the difference of charge between the plates of the capacitor. So we'll call this EI, being the electric field due to the insulating material. So therefore the strength of the electric field with the dielectric inserted is equal to E0 minus EI. Or we can write this as the original electric field without the dielectric reduced by some factor kappa, where kappa is greater than 1 and is a dielectric constant, which depends on the type of insulating material in the dielectric. So therefore from this we obtain kappa is equal to E0 on E. Now recall that the capacitance was equal to the charge on the voltage, and for a parallel plate capacitor it's the electric permittivity by the area of the plate on the separation between the plates. So this is the capacitance with the dielectric inserted. And before the dielectric was inserted, we'd have a capacitance C0 of Q, where the charge remains constant as we remove the power source on the initial change in electric potential, which is equal to the permittivity of free space by the area of the plate on the separation. So these don't change. And recall that we can write the change in electric potential in terms of the electric field. So what we have is E times D and E0 by D. And therefore if we divide these equations, what we get is the capacitance with the dielectric inserted on the original capacitance is equal to this expression on this expression which will give E naught on E. And that's equal to epsilon on epsilon naught. So as we can see, the dielectric constant from this relationship can be written as the electric permittivity with the dielectric inserted on the permittivity of free space. So if we're given that's equal to kappa, then this implies that the capacitance is equal to kappa by the capacitance without the dielectric. So given that kappa is greater than 1, then the capacitance increases with the presence of the dielectric. And assuming the general case, where the power source is connected, and the charge on the plates of the capacitor is no longer constant, the capacitance increases because the polarized electrons in a dielectric material act to repel electrons from the positively charged plate. So therefore that leaves behind more positive charge on that plate, and in this positively charged region, that's going to draw more electrons to the negatively charged plate. So that results in an increase in capacitance, regardless of whether the electric field got weaker. So given that we assumed that the charged capacitor was disconnected from the power supply to have this condition of constant charge to derive these relationships, in the case where the battery was connected, then the voltage would be constant, and recalling the relationship between the capacitance and the charge on the voltage, then for a given constant voltage, more charge will accumulate on the plate due to the presence of this polarized dielectric, and therefore the capacitance would increase. Now note that if the voltage was too high, then the relationship between the electric field and the voltage would give the electric field is the voltage on the separation between the plates, and therefore the electric field will be too strong. So that can result in electrons being ejected from the dielectric material towards a positive plate. And in that case, a hole would get burned in the dielectric and the capacitor will get discharged. So have a think about this. Suppose we have a conducting wire. So we have the electrons in the metal flying off at random velocities. So there's no ordered motion of these charge carriers through the wire. Now on the other hand, current is the rate at which the charge passes through the cross-sectional area of the wire. And this is the ordered motion of charge through a conductor, which is achieved by applying a potential difference through a power source. So we have the electrons flowing through the wire, and then they bump into the core atoms and the electrons in the wire, and therefore due to the potential difference, an electric field gets generated in the wire, and the electrons flow through the wire in an ordered way. So in other words, they have an average velocity, being the drift velocity. And this drift velocity is of the order of millimeters per second, because the electrons interact with the atoms and other electrons in the wire. So they get slowed down. Now if we take a section from this wire, so we have a cross-sectional area, and a length delta x, we have the current is the charge flowing through the cross-sectional area of the wire on a change in time. And if we denote n as the number of charge carriers per unit volume, then if we multiply this by the volume, then that gives the number of charges, and then multiplying by the charge that's carried by these charge carriers, we get delta Q. So delta x being the distance that the charge has to travel is equal to the velocity by the change in time. So let's replace this. And then dividing through by delta t, we get a relationship between the current and the average drift velocity. So noting the charge carriers in the wire are electrons, so Q would be minus E, where E is the elementary charge. And note that current has units of coulombs per second. So 1 coulomb per second is 1 ampere, or amp. So we can see that electric charge moves in a circuit in response to an electric potential difference. And this here is sometimes referred to as the electromotive force. So noting that a circuit is a conducting pathway through which electrons can flow. So here they flow from the anode to the cathode of our battery. And direct current is where the charge carriers travel in one direction, as in this case. And we see here that an electric field is sustained inside the conductor due to the potential difference maintained by the power source. So noting that EMF, or electromotive force, is not actually a force. It's the change in electric potential, which is effectively the work done per unit charge in volts. And note the analogy between conductors we looked at under electrostatic conditions, where we saw that excess charge resides on the surface of a conductor, and the conductor formed an equipotential surface. So that's different to this case, where you get the electromotive force driving an electric field through the conductor. And also note that if the current is 0 in a section of the wire, the net motion of the charge carriers is also 0. But note that the individual charge carriers will not have 0 speed. So the electrons still travel at random velocities, but they're just not moving in an ordered way through the conductor. We saw that current can be written as the charge by the number of charges per unit volume by the cross-sectional area through which they're flowing, multiplied by the average drift velocity. So the electrons move in an ordered way through the conducting wire due to the potential difference, or electromotive force, of the power source, which is denoted by epsilon. and noting that current is a scalar quantity. Then if we divide through by the cross-sectional area of the wire, so we have the charge by the number of charge carriers per unit volume by the cross-sectional area of the wire by the average drift velocity. And then if we consider the direction in which the current is flowing, then this quantity on the left with the direction is called the current density, which is equal to Q by N by the average drift velocity. So the current density is a vector quantity. So the current density is the flow of charge per unit area. And more generally, it's related to the current by the integral of the dot product between the current density and the area vector dA. So if the normal vector of this cross-sectional area points in the same direction as the drift velocity, then the cosine of the angle between them evaluates to 0. So therefore we can write this as the magnitude of the current density by the cross-sectional area of the wire. So recall that the potential difference across the conductor creates an electric field within that conductor, and the electric field is proportional to the resistivity of the conductor and the current density. And when we look at Ohm's law, we'll derive this, but qualitatively we can write this as the resistivity by the current per unit area, and we multiply this by a direction vector specifying the direction in which the current is flowing. So if we take the current as constant, then for a material with a higher resistance, a higher electric field would be required to maintain that same current or electron flow. And if the cross-sectional area of the wire is higher, then the electrons would have a higher space to move, and therefore you require a lower electric field to sustain that current. Now the current density can also be given as a function. So in that case, the total electric current through a section of wire can be obtained by integrating the dot product between the current density and the differential area vector. So recall we had a power source that creates a potential difference which can sustain an electric field inside a conductor. So therefore the current would be due to the electrons flowing against the direction of the electric field. But as we mentioned, current is a scalar quantity, which is a rate at which charge flows through a cross-sectional area of the wire or conductor. Well, we can observe that while it's a scalar, it still has a direction, because the electrons go from the anode and around to the cathode in a circuit. But because its direction is relative to the current carrier and not space, then current does not obey the laws of vector addition and doesn't have any vector components. And when solving problems involving electric circuits, we actually use conventional current being the direction in which positive charge would move. So that will be against the direction that the electrons are flowing. So they'll go from the cathode and back to the anode. And note that this is only a convention that we use. So positive charges would flow against the direction of negative charges. But always keep in mind, the current is actually due to the movement of electrons, or negative charge carriers. Even though you solve problems using conventional current. A homogeneous cylindrical rod carries a current with a current density J, and that varies with the radial distance from the center of the rod. According to this function, what is the total current in the rod? So remember that the total current was equal to the integral of the dot product between the current density vector and the area vector of the rod. And remember, the current density was related to the drift velocity using the charge by the number of charges per unit volume by the drift velocity. So at the middle of the rod, the velocity is going to be 0, but as we move away from the center up to the radius of the rod, the drift velocity is going to be higher. So therefore, if we take an element on this cross-sectional area, so we'll take a ring with some infinitesimal thickness, dr, and this has some radius r. So the current density on that ring is going to be 2r, being J, multiplied by 2 pi r, being the circumference of the ring by the thickness, which gives the area of that thin ring. And then we integrate this from r equals 0 to the radius of the cylinder to get the total current through that cross-sectional area. So taking the constants outside the integral, we have 4 pi, and the integral evaluates to r cubed on 3. Evaluated from 0 to r. And therefore the total current is 4 pi r cubed on 3. And note that the current density is in units of current per area, and this here is the infinitesimal area that we used. So our result will be in units of the current. So for example, coulombs per second or amps. An electric circuit is really the main application of electricity and magnetism. And a circuit is composed of electrical loops, and these loops can contain different components depending on the function that you want the circuit to perform. So here we have a battery or a power source and a switch, which allows us to turn this light bulb on and off. And you may also have a resistor in the circuit to prevent too much current flowing through this light bulb and blowing it up. Now an open electrical loop, such as this one, which is created by this open switch, does not allow charges to flow. So that's what we call an open circuit. And in contrast, if we close this switch, then we get a closed loop. So this closed circuit creates a pathway for charges to flow. So in this case, when the circuit is closed, current would flow through this light bulb and it will light up. Now on the other hand, if we create a short circuit by connecting these 2 points together, then you're basically shorting out the battery, because current flows through the path of least resistance. So therefore, instead of flowing this way through the switch, and note that when we refer to current, we use conventional current, which is the direction that positive charges would flow. But we know that current is due to the flow of electrons through the circuit, so keep that in mind. So because we created this short circuit, the current would flow along this path of least resistance, and therefore the bulb would not light up in this case. But instead, you get uncontrolled flow of current through the battery, and you'll short the battery, basically damaging it. And to prevent damage from such design errors, a fuse can be installed. So therefore, when you have too much current, the fuse will instead get damaged and stop the current from flowing. To prevent damage to a component in the circuit. And note that depending on your design, you may have multiple loops in a circuit. So for example, you may have a capacitor here. And now let's remove this short. So therefore in this case, a single circuit element, such as this resistor here, can be part of multiple electrical loops. And we'll look at more complex circuits as we progress. Circuit schematics are representations that are used to describe and analyze electric circuits. And the properties of a circuit are dependent on the physical arrangements of the constituent elements. Now, circuit elements have common symbols that are used to create schematic diagrams. And we've seen a symbol for a battery. So the longer line represents the cathode or positive terminal, and the shorter line represents the anode. And sometimes you may see a battery drawn as follows, using multiple long and short lines. And we've seen a symbol for a resistor. So this reduces the flow of current through a circuit. And this here is a symbol for a light bulb. And here we have a symbol for a switch. Now, other circuit elements you will encounter are capacitors. So these are represented as two parallel lines of equal length. And recall that the function of a capacitor is to store charge. And when we look at magnetism, you'll also come across inductors. So these are represented using a loop of wire as shown. And we'll also have measuring devices such as a voltmeter, which is represented schematically using a circle with a symbol V. So this is used to measure the potential difference between 2 points. So you typically connect it in parallel. And an ammeter is used to measure the current in a circuit. So that's represented with a circle and an A. So to measure the current in a circuit, you'd connect the ammeter in series. And remember that circuit diagrams will generally be drawn using conventional current, unless otherwise specified. So that means we look at the direction that positive charges would flow through the circuit. If this switch was closed, of course, or we have a closed loop for current to flow. But we know that current in a circuit is due to the motion of the electrons. So keep this difference in mind. And if we have a variable circuit element, then we draw a diagonal arrow across that standard symbol for that element. So this means we have a variable resistor that can be adjusted. And another example is if we have a variable capacitor that can be adjusted, then we draw a strike through arrow through that circuit element to represent it. One tool that I recommend you use is Tinkercad, and I'll leave the link below to this web application in the description. So this is a circuit simulator that allows you to design and experiment with your own circuits. And note that you generally use a breadboard to experiment with circuits. And we'll briefly look at how this works in Tinkercad. So as we can see, we have a breadboard with nodes or points to connect circuit elements, and the nodes or points in each of the top two rows are all connected to each other, but the rows are not connected to each other. And here we have a column of nodes from F to J, which are all connected, but each column is not connected to the neighboring column. And similarly here, we have a column with connected nodes A to E, but the columns are not connected to each other. And these two blocks of columns are also not connected. And finally, we have the bottom two rows, where the nodes in each separate row are connected, but the rows are not connected to each other. So therefore we can build our circuit by connecting the positive terminal of the battery to this row, where all the nodes are connected, and then we connect this row to the left terminal of the switch, and from the common terminal of the switch we connect that to this column where all the nodes are connected, and we connect this to the resistor, and then through the resistor we connect this column here to this column of nodes, to which we connect the terminal of the light bulb, and then through the light bulb we connect this column of nodes to this column. So basically we're going from resistor to light bulb and down to this column of nodes and to the negative terminal of the battery. So this row here is all connected to the negative terminal. So as you can see, we have a closed loop. So positive to switch, through the switch to the resistor, through the light bulb, and back to the negative terminal of the battery. So with this switch, if we flick it to the right, then the common pin and the right pin are engaged, and therefore we no longer have a closed loop for current to flow. So the switch shuts off the light bulb. So if we flick it to the left again, the light bulb lights up. And if we increase the resistance, then that reduces the flow of current through the light bulb, so you can see it gets dimmer. So if we go back to a lower resistance, the light bulb goes on. And we can also look at the schematic view So as we can see, we have the battery connected to the switch, and then the switch is connected to the resistor, which is connected to the light bulb. And that's connected to the negative terminal of the battery. So we see that when these two pins of the switch are touching, we'll have a closed loop. And if these two pins are touching, then we have an open loop and no current flows. So to create a short circuit, we can connect a wire from the positive terminal directly to the ground. So therefore, when this switch is on, the light bulb won't light up, because current would flow in this loop unimpeded and damage the battery. And you can also create a short in each component, so if these two pins were touching, then the light bulb would not light up, because the current will just flow straight through these points, because it's a path of least resistance. So therefore there's no current going into the bulb, as we can see, where we've shorted the light bulb. So if we delete this and run our simulation again, we can see the light bulb lights up. So try to build your own simple circuit in Tinkercad using the breadboard to have some practice testing out different designs. Resistance is a measure of the degree that an object opposes the movement of electric charge. So for example, if we attach some element to this circuit made of a certain material and close this circuit, then if this material was copper, then that's a conductor that easily allows electrons to flow through it. But if the material was glass fiber, then the current would be too small to measure. Because as we know, with a conductor, such as copper, the valence electrons are free to move around, whereas with an insulator, such as glass, the covalently bonded network solid won't allow electrons to flow through it. Now if we consider a resistor, which is a typical circuit element to stop the flow of current, and suppose it has a uniform geometry, so a constant cross-sectional area and a constant length, which will denote L, and the material that the resistor is made from also has a certain resistivity, which we denote ρ. So the resistance of this resistor is the resistivity multiplied by the length of the resistor on the cross-sectional area. So as you can imagine, higher resistivity, such as where we have an insulator, would result in a higher resistance. And if the resistor were longer, so there's a longer path for the charge to flow through it, so that would also increase the resistance. But a higher cross-sectional area would reduce the resistance, because as you can imagine, the charge will have a higher area to flow through, and is thereby less likely to bump into electrons that repel it. So effectively the resistance is proportional to the length of the resistor and inversely proportional to the cross-sectional area. So as an example, the resistivity of copper is 1.7 by 10 to the minus 8, and that's in units of ohm, meters. So note that the resistance is in ohms, and suppose the length is in meters, and the cross-sectional area would be in meters squared. So ohm meter per meter gives the resistance in ohms. And the resistivity of glass fiber is of the order of 10 to the 12 ohm meters. So you can see it's much higher than that of copper. So effectively, the resistivity of a material is a fundamental property of the material, which, as we saw, depends on the atomic and molecular structure, and quantifies how strongly the material opposes the motion of electric charge. And here we've depicted the motion of charge using conventional current. And note that the resistivity of a conductor increases with temperature. So for example, looking at the conductor, if you have a higher temperature, then the electrons would have a higher kinetic energy, then they're more likely to bump into charge that's flowing through this conductor. Now suppose we have a resistor with uniform geometry, so it has a constant cross-sectional area and length, but the resistivity varies along the length. So it's a function of L. So therefore, if we take some element that has a differential length dl, then using this formula for the resistance, the differential resistance is the resistivity as a function of L multiplied by dl on the cross-sectional area of the resistor. So that would be this area over here, which is constant. And therefore, if we integrate both sides, we obtain a total resistance of the resistor with uniform geometry. Ohm's law relates the current, resistance, and potential difference across a conductive element of a circuit. So note that Ohm's law is not a universal law, so not all circuit materials follow it. So it basically says that the current is proportional to the voltage across the element, or potential difference, and inversely proportional to the resistance. So the higher the resistance, the lower the current through the circuit element, and the higher the voltage, being the potential difference across the circuit element, then the higher the current. Now materials that obey Ohm's law have a constant resistance for all currents and are called ohmic materials. So in other words, the ratio of the voltage to the current is a constant. And an example of a non-ohmic material is a light bulb. So this doesn't obey Ohm's law. And an ohmic material has a constant resistivity. So recall, if the resistance is constant for a uniform material, then the resistivity must also be constant. And the resistivity is constant regardless of temperature. So note that resistors can convert electrical energy into thermal energy, and that may change the temperature of both the resistor and its environment. So as you can imagine, when the resistor dissipates electrical energy, it gets hot. So for an ohmic material, we can plot the current versus the voltage, and the slope of the current to the voltage is the reciprocal of the resistance, which is constant. So therefore the resistance of an ohmic circuit element can be determined from the slope of the graph of the current in the element as a function of the potential difference across the element. A cylindrical wire has a radius of 2 millimeters and a length of 1 meter. And it has a resistivity of 2 by 10 to the minus 8 ohm meters. Now if each end of the wire is attached to a 12 volt power supply, find the current. So recall by Ohm's law, the current is the voltage or change in electric potential across the element on the resistance. And the resistance is the resistivity, which is 2 by 10 to the minus 8 ohm meters, multiplied by the length of the wire, which is 1 meter, on the cross-sectional area, which is pi by 2 to the minus 3 meters squared. So we have consistent units. So the resistance is 1.592 by 10 to the minus 3 ohms. So if we substitute 12 volts and the resistance, we get the current, which is 7,539.8 amps, which is quite high. Now if the wire had a resistivity that varies according to the resistivity by L, so therefore the resistivity is a function of the length along the wire. Find an expression for the resistance in terms of the resistivity, the radius, and the length of the wire. So the total resistance is the integral of the resistivity as a function of L over the cross-sectional area of the wire integrated over L. So if we take a differential element along the length of this cylinder, which has a constant cross-sectional area and a differential length, then this element has a differential resistance dr. Then if we sum up these differential resistances across the length of the cylinder, then we get the total resistance. So therefore substituting for the resistivity as a function of L, we have ρ being a constant by L, and then if we take the constants outside the integral, being ρ on A, and integrating this expression, we get ρ on A by L squared on 2, evaluated from 0 to L. And therefore the resistance would be the resistivity by the length squared on 2 by the cross-sectional area. And the cross-sectional area of this cylinder is pi by the radius squared. So as you can imagine, for a longer wire, the total resistance is higher, and for a higher radius of the cylinder, the total resistance would be lower. the rate at which energy is transferred, converted, or dissipated by a circuit element is the electric power. So recall that power was the rate of work, and if this circuit is subjected to a change in electric potential due to a battery, for example, then the potential energy of a positive charge carrier is going to drop across a circuit element over some time t. So the electric potential energy is transformed into light and heat in the case of a light bulb, or dissipated as thermal energy or heat by a resistor. So we can write the electric power is the change in electric potential energy. So we have the positive charge carrier by the change in electric potential or voltage, and this change occurs over some time interval. So for a given change in electric potential, we can take this outside, and therefore we have delta V by delta Q on delta T. And delta Q on delta T is the current. So we can write the electric power as the current by the voltage. So the electric power is the rate at which electric potential energy is transferred. So for an ohmic circuit element, such as a resistor, which has some constant resistance, then we can use Ohm's law. So recall that the current is the voltage on the resistance. So for the resistor, we can write the electric power as the voltage squared on the resistance, or if we instead substitute for the voltage, we can write this as the current squared by the resistance. And note that the power will be in joules per second or watts. So noting the current is in coulombs per second and the voltage is in joules per coulomb. So in the case of a resistor, the electric potential energy is dissipated as thermal energy or heat. So the resistor becomes hot when the current passes through it. And as you can imagine, the brightness of a light bulb increases with power. So power can be used to qualitatively predict the brightness of light bulbs in a circuit.